Am I the first one? Just performing a test.
And what's the,
It's starting to take shape. See what it's going to be. What a good explanation is going to be. Yeah, that I'm basically.
so what's the schedule?
Aside with some.
And Lisa. And those are the only two people who are logged in.
Have you got on the screen when the Zoom room and all that?
Except that, so it's Ben and Alexey at the beginning, I think. And Ben's not here and Alexei's not here, which is why what's the schedule? I just had that. Yeah, so it's Ben followed by Alexey and Vitaly, and then Nil and Hedra.
Anyone who knows Ben. knows
Oh,
it's
here's
not starting
chat.
On time.
Where, oh. They need to be let in and I don't have that, so it must be Lisa who has to let people in.
I bet you have lots of stories. From here.
That was fun ride. Osmo, tiny, like,
Osmo?
yeah.
He's on Bathroom.
Yeah, yeah.
I haven't seen him in a few years.
Well, Ben's not, and see, I think Lisa,
So they made copyrighted. Copyrighted. Yeah. I'm here, this is here. This is another long way down. Are you presenting? You just waiting? Are you presenting? I'm not presenting this time. I am not. I am not. Just enjoy it. I can spot. Yeah, I'm really excited. It's supposed to be very complex. The professor I'm collaborating with, very long. Yeah. But he's presenting a paper, I don't know which day, but, nice one. The ownability of AI.
You're working it out with them, are you?
with Lisa,
Gonna
who's
get
letting people in.
Haley or something up here to get started.
So Lisa needs to let people into the Zoom room. That's what's going on.
Okay.
She just, because Hedra was trying to get in and Mills like, she can't get in. And Lisa said, hey, Matt, I'm here. And yes, I'm letting people in. And I was writing her saying, hey, are you letting people in?
Reality is a society, right? That has to be like a property.
So it's Ben followed by Alexey and Vitaly, followed by Nil this morning.
Really is important.
Should we-
And Nil is here. The workshops luckily are not as difficult to fit into the time. Like,
Yeah.
so today I'm not as worried. So I'm just kind of meeting people.
So we've unmuted us. We're live at AGI-22 at OpenCog Hyperon Workshop 1. Thank you, folks. I'm going to leave this huddle for now, right? Have a beautiful day. Bye. Welcome online, everyone who's here for Hyperon Workshop. Let me tell everyone. We're live. AGI-22 is live, coming to you from in Seattle. Ready to kick off with Dr. Goertzel, followed by Dr. Alexey Potopav. And Dr. Clay is here looking at me, and I'm saying the right thing. Welcome, everybody. We're just ready to kick off. Please give us 2 more minutes on YouTube. We're just coming. We're just getting them. Thank you.
Hey, everybody, welcome to AGI-22. We're going to start in just a couple minutes. Today is the first of 4 full days and the latest and greatest in AGI and building the decentralized singularity. You are here for the workshop with Ben Goertzel and Alexey Potopav, which is scaling up Neural-Symbolic AGI with OpenCog Hyperon. They're going to talk about distributed Atomspace, probabilistic logic network, temporal reasoning, an overview of the general theory of open-ended intelligence based on a neural-symbolic cognitive architecture. And we're going to be right back with Ben Goertzel himself any minute. So welcome, and we'll see you very soon.
And you're up.
I cannot. Is the camera working and stuff? Okay. Where am I on here? Which,
So you're
well, that's you. I don't see myself. I don't, okay. This is not sensitive positions. It should be actually showing my head. This camera. All right. So that
like you have to look at what subgroups of humanity are actually.
Good morning, everyone. So welcome to the AGI-22 conference and to this workshop on scaling up neural-symbolic and neural-symbolic evolutionary AI methods toward AGI. I mean, in large part, this is a workshop on OpenCog Hyperon and our work to sort of rebuild the OpenCog system into something that can credibly serve as a platform for the first real AGI. But we don't want to make the workshop really just about this specific name brand system that we're building. I mean, it's really about the collection of ideas and algorithms and structures and so forth, which we're gathering together into this new version of OpenCog. And we did a workshop on this last year at the last AGI conference, and a lot of the same people involved and a lot of the same ideas involved. I would say the difference this year is there's been a bunch more code written and there's more papers written, and we've gone a decent length toward concretizing the ideas that we discussed a year ago. We're not yet there to having like a fully mature system that we can use to implement the world's first AGI, but I think I'd say we have preliminary evidence that at least the direction we're going like can be implemented and with the current state of technology, and this isn't totally fanciful. And we've fleshed out in the minds of the folks working together on OpenCog Hyperon, we've fleshed out a bunch what it is we're trying to do. So I think as opposed to last year in this workshop, the flavor was more like here's what we've been scheming and what we're planning to do. Now the flavor, here's what we're in the middle of doing, and here's some of the preliminary results that we have. Now hopefully next year we'll have more of a mature system and some interesting proto AGI results using Hyperon, which we don't have now, but at least we're getting there. We're actually working on it. We're starting to implement machine reasoning and so forth in prototype Hyperon systems. So most of this workshop is going to be pretty concrete and nitty-gritty presentations on the software structures, the math behind the software, and so forth that we're working on. I'm going to give more of a high-level overview of the motivations and ideas that led us to start moving in this direction. Now, I did the same thing last year, and I was tempted to just dig up the slide deck from last year and give the same talk, because I mean the high level motivation and inspirations haven't really changed too much. I mean, we're open to revising anything based on experience, but we just haven't gotten to the point yet where we can prove our initial ideas wrong, right? So instead, what I decided to do is not use a slide deck this time around, and just go over the same ideas as sort of quasi stream of consciousness, just figuring we can create a different video artifact this way, since we have a structured version going through the presentation deck already from last year. So I want to start, as I did last year, start from original motivation for what kind of system we're building, which is like, what is thinking, what is a mind, right? And go through a series of steps leading you from notions about what is thinking and intelligence, leading you up to a very specific set of mathematical and software systems which we're implementing. And obviously that's a long journey, which in like half an hour I'm only going to be able to very lightly summarize. There was a paper I posted on Archive in late 2020, I think it was. It could have been early 2021, called The General Theory of General Intelligence, which is probably 60 pages, and in itself is a sort of extended abstract for a whole bunch of other papers that it references into. So to dig in more depth into the whole intellectual journey I'm going to describe here, you can look at that paper, follow up the references in that paper. I also recorded a like 10-part video series of me talking about each section of that paper, which is like 6 or 7 hours of video altogether, which I think was recorded mostly late at night when I was half asleep. So I've never watched it. I'm not sure what the quality is, but it does go through that whole 60-page paper step by step. For those who, for some reason, prefer watching videos to reading, I'm not one of those. I can't stand watching videos, but I'm a dinosaur by now. So let's start now, as the paper on general theory of general intelligence does. Let's start with what is a mind, what is thinking, and I even want to start before that with like, what is existence? What is the universe at all, right? And Joe Shabak is going to give a keynote on that topic on Sunday. Actually, his title is "It from No Bit," like the universe from the standpoint of AGI. I want to start, and that's a play on "It from Bit," which is a paper by John Wheeler on sort of how observation brings the universe to life in quantum mechanics. I want to start instead with the philosopher Charles Sanders Peirce and his sort of metaphysics and ontology. And Peirce divided the existence into 3 categories, which he called very poetically first, second, and third. Right? If he was more Zen, he would have started with 0, right? With the pearly formless void. Right? On the other hand, not naming that, maybe more in the spirit of Zen, right? And you could go beyond that. I mean, Carl Jung, in his own ontology, had sort of archetypal categories corresponding to each number. So you can go to 4th, 5th, and 6th. But we'll start with 1, 2, and 3. And Peirce's first, what he meant is like raw experience, what you would call qualia, right? Just being, like the sense of looking at red or something, without analyzing it or relating it to anything. Peirce's second basically corresponds to reaction, like a billiard ball knocking another billiard ball, which is sort of how we looked at reflex reactions or Newtonian physics or something. Peirce's third is relationship, like A is a relation between B and C. Then, if you want to continue numerical archetypes, in Jungian ontology, fourth is where you get to synergy and emergence, where you have sort of a holistic combination of multiple relationships, and you can keep going from there. But if we stick with first, second, and third, we already have a sort of paradigm for thinking about aspects of the mind. Pure consciousness and experience, in Peirce's view, is firstness. It is just in a different category from patterns and relationships. And second is physics, viewing the mind as a set of reactions and actions. And third is relationships. And when you get into relationships, then you're looking at patterns, you're looking at models of computation and programs and so forth. These are all about relations between different things. And Peirce showed in a way that any complex network of n-ary relations, like you have relations between 20 different things, you can reduce them to a collection of thirds of basically f of AB, right? So if you have f of A, B, C, D, E, F, G, you can boil it down to a bunch of f of A, B ternary relationships. That's now commonplace. I mean, Peirce basically invented quantifier logic and universal and existential quantifiers and all that. So but back at the end of the 1800s, when he was thinking about this stuff was not considered so obvious. Now, of course, that's sort of saying that from the standpoint of third, higher order things can be reduced to third. You could say from the standpoint of first, everything is reduced to first also, like in a way, everything is projected into experience, right? From the standpoint of physics, everything is projected into physics. You can look at the hard problem of consciousness, as David Chalmers articulated it, as basically how to reduce third to first, basically. And like, how do you reduce the view of the world as network of relationships and the view of the world as raw, unprocessed experience? And of course, Peirce's view would be, well, you don't, right? These are just different basic ontological categories, and you don't collapse one to the other. They each are what they are. And one to collapse everything into one category is just a diluted way of thinking, basically. So starting from this high level view of things, when we then want to understand mind from a sort of scientific perspective, you're mostly looking in Peirce's category of third. That doesn't mean that consciousness and experience are ruled out and not interesting or something. It just means that's not the level that you're looking at when you're thinking about like analyzing how a brain works or analyzing how to build a thinking machine or something. And one can then introduce notions like pattern and computation. And I spent a bunch of time early in my career trying to formalize sort of what is a pattern? What does it mean to identify a pattern? And of course, a pattern is a sort of relationship. It's a sort of representation, right? And the notion of what is a representation, you can dig into forever, right? So a book from the 90s I'd recommend is On the Origin of Objects by Brian Cantwell Smith. And he's going over in great detail, what is it to identify an object, right? So the hard part of 1 + 1 = 2 isn't the addition. The hard part is how do you identify a stable object and so that you can say there's one of that object in the world in the first place, right? And a young baby's mind takes a long time to get it to that point, to see that like when one object passes behind another one and comes out the other side, it's still the same object. That's still that same one, right? So this phone is a one that you could include and say 1 + 1 = 2. But a 1-month-old baby doesn't look at it that way. They look at it like it's one thing over there and it's another thing over here. We instinctively look at it like it's the same one object, right? So, but getting to that point, you're representing a recurrent pattern, and a representation is like a representation, right? So it's like you're storing in your memory the imprint of that phone when it disappeared. So that when the phone appears again, like that imprint of the phone in your memory is popping up again. It's presenting itself again to help you model the new appearance of the phone, right? And so this basic foundation of what a mind is has to do with having a memory and being able to, look at new combinations of sense data as representations in some sense of the old combinations of sense data. And then in that sense, representation and knowledge representation is the very foundation, even before you get to cognitive architectures, learning algorithms and all that. You can look at a pattern then as a representation as something simpler. So you're trying to represent something you've seen in some other form, which is then in some sense simpler than just storing the sense data. Because if you're representing the data of this phone that you see just as the pixels that came into your eye or something, then well, that's not exactly the same as the phone when it appears over here, right? It's a different angle. There's different things behind it. The light is slightly different. So if you're really just storing the exact sense data, it's not the same phone over here as over here, right? So to recognize it as the same phone over here as over here, there's some level of abstraction that's taking place. So when you're representing, you're imprinting this phone in your memory so that you can recognize it as the same phone over here as over there. You're representing it actually a little differently than the original phone. You're abstracting it in some form so that you can then recognize the phone over here as being in some way the same thing. And for every purpose, it's not the same thing, right? Like if you're concerned about whether it's going to get water dripped on it from the ceiling, it's actually different over here because it's in a different place. But for many purposes, it's the same thing. And here's where you start getting to a bunch of interesting learning theory, because I mean, there's various senses in which if you want a representation, like a transformed version of this phone, transformed version of a bunch of sense data to be useful in a bunch of different contexts, then having the transformed version be simpler in some sense than the original thing is useful. And then you can go through a whole bunch of detail, like what's the sense of simplicity in which having a simpler representation makes a representation that generalizes among more contexts. Like then you can try to say what's an axiomatic theory of simplicity that lets you make all the theorems about simplicity leads to generalization work, right? So you're confronting all these things at a very basic level of like, what does it mean to have a pattern? What does it mean to have a representation? What does it mean to have a representation as something that's simpler in some sense? And in the paper on general theory of general intelligence, I point to a bunch of other papers that try to go through sort of simplicity theory and pattern theory and trying to unravel all this. So once you go through all that, you come up with a perspective that I would call patternism. And I think that Ray Kurzweil uses the same term in his books. He views the mind as a mind as a system of patterns associated with an agent doing stuff in a world, right? And so it's a set of patterns which are interconnected to each other, which means that there are patterns connecting them. And this set of patterns is associated with some agent or system that is carrying out actions in some world. And once you get to that level, then you start talking about the things that preoccupy, cognitive systems theories, cognitive scientists. Now, at the core level of sort of philosophy of mind, I concluded there are two sort of meta dynamics underlying intelligent systems. One is evolution. One is what systems theorists call autopoiesis, which is sort of like self-organizing, self-rebuilding, self-reconstruction. And I mean, you can look at these as being and becoming in a Hegel philosophy sense, or you could look at it as individuation and self-transcendence in a postmodern philosophy lingo, which is reused in Weaver's work on open-ended intelligence that I'll come to later. So pretty much evolution is about taking what patterns that exist, mutating them or recombining them with each other, right? Mutation and crossover at an abstract level. And that's how new things get created. They don't pop out of the void. They come by recombining and mutating things that existed before, which is a theme that will come up on Sunday in our workshop on machine creativity, right? When you look at machine creativity, human or machine creativity really are about mutating and recombining what came before, but you need to mutate and combine them in the right way, right? And current deep neural nets doing creativity are mutating and recombining what came before on the very surface level. Whereas if you mutate and recombine what came before at the level of a deeper representation, then you're getting more fundamental creativity, more like people are doing. But it's still evolution, which is a slow, messy, nasty process. But that's what created us. That's what created all of our technology. Autopoiesis is about how does a complex system of patterns survive, right? And how does it survive? It survives by rebuilding and repairing itself constantly in adaptive interaction with its environment. Like when something becomes obsolete or something breaks, other parts of the system have to replace, rebuild, or improve it, right? This is what a biological cell does. It's what a biological organism does. It's what a human mind does as it grows and develops. So these are like meta dynamics. You have to have them there, or you don't really have a sort of living mind system. And in this sense, I think, GPT-3 has really neither evolution nor autopoiesis, right? So these are like very interesting artifacts that are being built in the deep neural net community now, and they may be able to serve as components of intelligent systems, but I think they're lacking both of the core dynamics of intelligence that you see when you dig deep into philosophy of mind. Whether you could vary on these algorithm systems in some way, like take these as a core for something that does evolution and autopoiesis, is a different question. I think there's serious obstacles there, but it's not on the face of it impossible, right? You can then ask, how are the networks of patterns that constitute a mind structured and laid out? And then in my second book, The Evolving Mind from 93 or something like that, I made an argument that across biology as well as cognitive science, you have a sort of overlaying of hierarchical network structure with hierarchical or associative network structure. And a hierarchical network and a hierarchical associative network are sort of coordinated with each other. And hierarchical is sort of like patterns among those patterns, patterns among those patterns, patterns among those patterns, and sort of directed a cyclic graph of patterns. And that sort of naturally falls out of the definition of pattern. And you can, if you look at the math of it, it comes out of like associativity of operations of combining things and so forth. So if you can combine processes to form new processes using an operation that's associative, then you naturally get a sort of hierarchy of patterns out of it. So there's deep algebraic roots that go into like Whitehead's process philosophy and so forth. And then hierarchy is just about association, right? It's about some patterns are similar to other patterns and more similar than they are to other ones. So you're getting a sort of metric space structure on patterns by saying which patterns are closer to other ones. But again, that aligns with hierarchy, because if you have patterns that are composed of subpatterns, other pattern may be composed of an overlapping set of subpatterns, and you can put a metric on there using a symmetric difference and so forth. So you get a hierarchy and hierarchy network at a very, very, very basic abstract level here. And I think this is another thing that pops up in the deep neural net world a lot, like hierarchy is important. And it clearly is. It's important in our physical universe, but it's even deeper thing than the physical universe. It has to do with pattern networks on the associative algebra. So hierarchy is very important. It's a very abstract general thing that has nothing to do with neurons, right? I mean, you can have hierarchy in a collection of logic propositions. You can have hierarchy in a collection of computer subprograms, but hierarchy and associativity are both really important things, and they pop up at all different levels. I mean, another key theme you get here is sort of recursive self-representation, which is where you have a system that in some sense tried to recognize its own self as a pattern in its interactions with its environment. And of course, human minds do this in a more sophisticated way than, say, simpler biological organisms. We have an explicit model of ourselves and who we are based on our interaction with an environment. But even an amoeba or a bacteria is forming some implicit model of its environment and itself in the combinations of chemicals that's spatially distributed inside that cell. This sort of recursive self-modeling is important for individuation and autopoiesis, right? So for a system to maintain its integrity as a system and rebuild itself and reproduce itself, having some implicit or explicit model of itself is a highly valuable strategy. So what you find is those pattern systems that can model themselves on the whole will survive longer than the ones that can't. So that comes about. And then the notion of cognitive synergy, as I've articulated in OpenCog and other AGI systems, also pops up at this very deep philosophical level. And that if you have a pattern network with many different sub-processes in it that are doing different sorts of things, I mean, it could be, in a bacterium, it could be eating one kind of chemical versus eating another kind of chemical versus moving, right? Or in a human mind, it could be perception versus movement versus long-term memory. If you have a bunch of different subsystems in an intelligent system or in just an agent doing things, and you have limited resources for that system, which is generally the case in our branch of the multiverse, right? I mean, in the physical world, you're struggling with limitations of energy or time or space or something. So if you have a bunch of different processes in your pattern system with limited resources, you're going to survive better if the processes can help each other out rather than working at odds against each other. And to help each other out, it helps if they know what each other are doing, right? So if, like in your bacterium, if the moving process and the nutrient ingesting process and the waste excreting process can all help each other out when they get stuck, and they can all, then if they have some insight into each other's intermediate state, they're going to be able to help each other out better when they get stuck, right? So this sort of follows from doing complex things under limited resources. And this pretty much leads you to what I've called cognitive synergy, that if you have multiple sort of dynamic subnetworks in a organismic sort of pattern network, if they can work together and they can perceive each other's internal intermediate states as they do stuff, on the whole, they're going to be more efficient than if you have a sort of collection of sub-processes that are operating independently and don't know what they're doing. You also find it's more complex to figure out how to make a collection of interoperating subsystems than modular subsystems. If you have infinite resources, then it's unnecessary. But in physical world, you don't, right? So this is sort of a herky-jerky hurdle through philosophical foundations. But the point I've tried to make is a lot of key points that come up in very concrete AGI system design actually exist even before you get to physics or computer programs. Like a lot of these things reflect philosophy of mind. And this is a point that Pei Wang, who's doing the NARS workshop now, has often made, is that if you get philosophy of mind wrong, probably you're going to fuck up in building an AGI system. Not necessarily. I mean, serendipity is the thing, right? And you could just happen on an AGI system that works by dumb luck, which is actually intelligence on the part of the global brain that you're embedded in, right? Like ingesting smart things that other people did in a way that you don't fully understand, but this happens to work, and you're going on some intuition. So you could get it right by mistake, and probably you're more likely to get it right by mistake if you have no philosophy of mind. But going on the wrong philosophy of mind will more likely to be fatal for building an AGI system. And what Pei and I have felt for a long time is a lot of the work toward AGI or strong AI is either based on no thinking about how minds work or based on wrong thinking about how minds work. And I think in our generation, because computers were very slow when we started our careers and AI software was very annoying to write, we had a lot of time to think about the foundations of how thinking works and how to bake that into an AGI design. I think for people coming into the field now, on the one hand, it's more exciting because it means you're less likely to like take 5 years and think about how does the mind work before writing your code. And there's pluses and minuses to everything, right? I mean, the minus of thinking a long time is you can like go down a mental masturbation sinkhole and just think amusing thoughts that don't lead anywhere. The plus is, in the optimal case, you can have a very well thought out framework by the time you start implementing and experimenting stuff, which can be an advantage. Because what I see now is most work in the AI field, and even most people trying to do AGI, are falling into the pattern of doing whatever's easiest to do with the tool chain that's currently available on to download from the internet, right? But that tool chain was mostly not built for AGI purposes. So you're trying to use a tool chain that's built for various commercial or practical purposes, and doing whatever's easiest to do using those tools. If you're starting from a deeper philosophical understanding of what you want to do, then you're thinking more like, let's use these tools where we can, but there's something you need to do that the tools don't do. How do we build the tool that will fill in that gap, which is sort of what leads to OpenCog Hyperon and so forth, which is a tool that I think fills a gap in the current ecosystem of tools. But another objective there is to be able to use all the existing tool chains better than the old version of OpenCog did. So taking the next step toward concrete stuff from philosophy, you get into algorithms, data structures, and computing theory, right? And here I'm just going to allude to a couple of things because I took up so much time on philosophy. I mean, I had a paper that was referenced in the General Theory of General Intelligence paper on combinatory model of computing. Like you can, there's a lot of different universal models of computing, right? That's not interesting. It was interesting in the 30s, 40s, and 50s. Now it's not that interesting anymore to say you have a new universal Turing capable model of computing. But one of the models of computing that's appealed to me is a chemistry type model where you say, I have a bunch of agents or artificial chemicals, whatever you want to call them. Two of them can combine to form a new thing. That new product can then combine with something else to form a new thing. And this sort of chemical reaction network is a universal model of computing also, if it obeys a very certain property. So you could look at the mind as a sort of set of cognitive chunks that combine with each other to produce new cognitive chunks, some self-organizing system. And this has universal Turing capability. It's an interesting model of mind for formalizing networks of patterns and evolution and autopoiesis and all this. And this ties in with a bunch of funky math regarding category theory and higher order categories and infinity groupoids and all this, because you're looking, in a way, you're looking at processes or programs that can produce each other. You're looking at programs for producing programs, programs for producing programs for producing programs. And there's a sort of ternary relationship between programs or processes, categories as abstract ways of modeling transformations, and then logics as a way of producing proofs given axioms. There's a bunch of equivalences between programs, categories, and proofs in logics, and you can look at equivalences between sort of higher order functions in programming language, so programs to make programs to make programs to make programs, and higher order categories of categories of categories, and then logics for proving things about logics, for proving things about logics, and you can then take that up to the infinity level, and you get a bunch of stuff, weird stuff about infinity groupoids, and how useful that is, we could debate at length, but Jonathan Worrell, who's here at the workshop, and I did some work with Alexey Potopav and others, formalizing some aspects of the semantics of OpenCog Hyperon's meta language using these basically stuff that maps into these infinity groupoids and cubable categories and so forth. So that some of this wacky abstract math that comes out of an attempt to formalize patterns and relationships and computations, to me at least, appeared to be useful in formalizing the languages that we're developing within OpenCog Hyperon. That will be a whole talk in itself, and Jonathan gave some of that talk at last year's AGI conference. So you can find the video on that stuff. The nature of graph, hypergraph, and metagraph representations plays in here also. And going back to the philosophy, I had a paper on distinction graphs in 2017 on the ArcSci, which is sort of looking at the most basic mathematical operation you could put in place to model experience is distinction, like making a distinction between one thing or another. And you can look at that as symmetrical or asymmetric, just perceiving a difference between something else. And then if you want to have a very interesting headache, go back to the book by Gilles Deleuze, the postmodern philosopher, Difference and Repetition, which is a book early in his career, where he's like looking at what does it mean to say two things are different? How do you get to the point of saying that one thing is a representation of it? So it's going back to object permanence and that the phone disappearing and reappearing. And so he's looking at it from a foundational view. What does it mean to be able to say there are two things and one thing can be different from another, right? So you can look at that as a basic operation and say, what does it mean to say this thing is different from that thing? Then you can look at that as a directed arrow, right? So you have one node and then an arrow from another thing, meaning those two things are different. You can then build up directed graphs out of that. And so in that way, you're building up directed graphs out of phenomenology, basically. Then you can build up directed graphs, symmetric graphs, then you build up to labeled graphs or hypergraphs, which have links pointing to more than one node. Metagraphs, which are like hypergraphs, can have links pointing to links and links pointing to whole subgraphs. So you can tell a story, which I do in the paper on distinction graphs, of how you build up to these metagraphs step by step from raw experience, beginning with just one directed link, which represents a perceived difference. You could also look at graphs from a totally different point of view. If you start with like computing theory or logics, you can use graphs to model semantic networks as a model of logic, or you can use graphs to model the states of a computing machine. And one of the things I decided in the late 90s is, in terms of bridging all this philosophy and math with what computers can actually do, graph models, hypergraph models, metagraph models are an interesting structure to work with. I mean, they're not the only way to do it. Like if you were evolving soups of chemicals to be a general intelligence, you'd be looking at some continuous variable model instead. But given that we're working in these discrete computers, a graph is a nice structure. And most work in AI now is on matrices and matrix multiplication and matrix inversion and so forth. Matrix is also a nice data structure. I think matrix is an especially nice data structure for processing sense data from physics, because I mean, you get an array coming in through a camera and it's naturally worked from a matrix. And if you're doing Fourier transform of audio or something, matrix math is natural. I feel if you're dealing with language or reasoning or the more abstract parts of the mind, the more abstract ways the mind represents something, a couple of steps of abstraction away from sense data, a graph becomes a more natural representation than a matrix. Of course, graphs, hypergraphs, metagraphs can be represented as sparse matrices, right? So I mean, it's all in the end, it can be interconverted, but again, you have to be wary of equivalences that don't take into account computational efficiency, because this is something I'll come to a little later. But if you set aside computational efficiency, there's a decent argument you could make an infinitely intelligent AGI in like 50 lines of Lisp code or something, right? So saying that graphs and matrices are the same, setting aside efficiency, isn't necessarily interesting, because making a general intelligence that can operate in the real world is largely about dealing with energetic time and space resource limitations, right? So I think a graph is an interesting mode of representation to use. It maps very naturally into phenomenology of experience. It matches naturally into models of computing and logic and pattern and so forth. And when I started working with hypergraphs and metagraphs for AGI in the late 90s, it was quite an obscure thing to do. Like when Andre Senna and Thiago Meye, Cassio Panachin and myself coded the first OpenCog Atomspace in 2001, building on WebMind's node and link graph we made in 97, there were not a lot of knowledge graphs being built for AI then. I mean, there was papers on semantic networks. Now I think graphs are much better accepted. You have people making deep neural nets using a knowledge graph as the long-term memory. You have graph neural networks. It's sort of, you have stuff like Neo4j, like you have graph data stores being big commercial things. I think it's still underappreciated, and partly because we don't have a good tool chain for it compared to matrices. So one thing that we're going to talk about later in this conference is Rachel St. Clair and I are working on optimized hardware for metagraph manipulation. So we're making a basically AGI board where you have deep neural net chip, which is basically souped up GPU for deep neural nets. You have a CPU, you have a chip Rachel has designed, which is for accelerated hypervector manipulation. So for manipulating large sparse bit vectors, which is useful in OpenCog for episodic memory and other things we'll talk about a little later. But then you have a chip I designed, which is for optimized pattern matching on large metagraphs. So I think you can put pattern matching on metagraphs at the chip level in MIMD parallel processor and RAM architecture. And then that can perhaps accelerate graph-based AI in the same way that GPUs have accelerated matrix-based AI. So I think that the importance of graphs and metagraphs is at a pretty deep level, in a way that's, you could argue in a lot of ways, that's the most natural discrete representation of a lot of these philosophical things that we've been discussing. And working closer to Hyperon now, I had a paper in 2020 on folding and unfolding on metagraphs, where I argued if you take the fold and unfold operators from functional programming, which I went over in my slides from my talk last year a bit about how they work. I'm not going to try to hand wave it, but if you take fold and unfold, which are typically done on lists or trees, but you can do them on graphs also. And there's papers I'm doing it on graphs. I extended that to metagraphs, which is kind of straightforward. What I argued is that most of the operations you need to do to make an AGI system, you can boil down to various fancy fold and unfold operations, anamorphisms, catamorphisms, other operations for the morphisms on metagraphs. And this becomes interesting because if it's to the extent it's true, it means if you can make an AGI infrastructure that's efficient for folding and unfolding stuff across metagraphs in a fancy way, then you have an efficient infrastructure for all the AGI algorithms that you want. Like, so in terms of a chip infrastructure, if your chip makes folding and unfolding across metagraphs on the chip efficient, right? Then that means you've made efficient the core operations you need for an AGI system. In the same way that if you can make matrix multiplication efficient on your GPU, then you've made everything efficient that you need for your deep neural net efficient, right? So you like matrix inversion, okay, well, do an iterative algorithm does as iterative multiplications, right? So we're doing something similar with trying to boil down cognitive algorithms into folding and folding on metagraphs. So this goes up into this goes down to a bunch of other math. So there's notional Galois connections that I talked about in my keynote in the workshop last year, and there's basically some theories showing if you have a variety of different algorithms can be boiled down using a bunch of math called Galois connections into fold and unfold operations. And in particular, if you know what dynamic programming is from Richard Bellman and so forth. So if you're familiar with Dijkstra's algorithm for finding the shortest path in a graph, that's the most common example of dynamic programming. Like you're trying to find the shortest path from one point to another, or sort of exploring a bunch of different paths and throwing out the ones that seem too long and continuing the ones that seem promising. And it's a quadratic time algorithm. It's very slow, but it will definitely find you the shortest path between two graphs by sort of following each path as long as it needs to be. You can then look at approximate stochastic dynamic programming, which means you're not trying to find the absolute shortest path, but just an almost shortest path. And it's okay if you're wrong a certain percent of the time. So I convinced myself that pretty much all algorithms you need for AGI could be formulated as approximate stochastic dynamic programming, which is one of those things that seems like an insight at first, then you realize it's completely obvious and not interesting. But in a way, it's interesting because you can take approximate stochastic dynamic programming and use Galois connections to boil down approximate stochastic dynamic programming to folding and unfolding, right? So if you have cognitive algorithms on metagraphs, you can boil them all down to approximate stochastic dynamic programming on metagraphs and use Galois connections to then boil them down to folding and unfolding on metagraphs. Then you have a software and hardware infrastructure that lets you do folding and unfolding in metagraphs efficiently, right? And then you've got it, right? So that's laid out in a paper called Patterns of Cognition from early 2021, which is summarized in general theory of general intelligence. And of course, this is all a lot of stuff to sift through. On the other hand, like it's probably less math in detail than you need to know how to build a semiconductor chip or something, right? I mean, building complex stuff, there's just a lot of different pieces that interlock together. Now, all that I've talked about so far is quite generic and would apply, to a human, to a dolphin, to a super intelligent killer lawnmower, to presumably the aliens evolved on some other planet or something, right? So then there's to an AGI theorem prover that just lived in math universe and did nothing but prove theorems. So another line of thinking that's important is what's particular about human cognition, right? So an AGI in general is much more general than the human mind. I mean, it doesn't take much thinking to realize humans are not the most general possible general intelligence. In fact, we're probably near the minimum level of general intelligence need to be considered like a robust general intelligence. We're about the stupidest possible general intelligence. We're just barely at the point that we can fully understand how stupid we are, which is important, right? Because it means we can see that we want to improve ourselves and replace ourselves and so forth. I mean, we're probably we're maybe the first organism on Earth to, in a useful sense, be universal Turing machines, right? I mean, in theory, maybe a bacterium or a mouse is, but they're not able to leverage that in what they're evolved to do, and we're able to leverage it. And maybe only a small percent of the human population, given education systems and how people think, right? So, I mean, we're certainly not the most possible general intelligence. If you ask me to run a maze in 750 dimensions, I'll get into a corner like very, very rapidly and not be able to get. I can't even do 4-dimensional chess. I can barely do 3-dimensional chess, right? Or 2-dimensional chess, 1-dimensional maybe. So we're a very particular kind of intelligence system. On the other hand, we're very interesting to ourselves. And beyond that, if we want to train an AGI and teach it and bring it up from baby stage to a mature stage, having an AGI system that we can understand and communicate with and that can live in our world and learn from our world has a practical advantage, right? So even if we're not attached to the human-like architecture as a particular kind of AGI, emotionally or philosophically, just on a pragmatic basis, if I want to debug a system that has a radically different architecture than humans versus one that's a bit like humans, there's an advantage to something I can understand. So then you come down to the question of what do you fundamentally need to emulate about humans to make an AGI human-like? I mean, given that we're not doing like a molecular level simulation of the human brain, which would be very interesting, but we don't have the technology to do it yet, nor the brain imaging to know how the brain works well enough to do it, right? So I came down then to something I called the mind-world correspondence principle, which is really a conjecture that I have some hand-wavy direction of a proof for and haven't proved. But the idea there is, if you have a system that's trying to achieve certain goals in certain environments, and these environments have certain symmetries or patterns relative to those goals, then the system, to be able to achieve these goals in these environments under limited resources, will do better if it has some version of these same symmetries and patterns inside itself. And the most commonplace example of that now would be if you have an agent that with limited resources is trying to do stuff in the hierarchically structured world, that agent will do it better if it imitates that hierarchical structure inside its own mind somehow. And I mean, you can see that in ways that are now obvious and well-known in visual and auditory cortex, right? Like we're humans and other animals trying to do stuff in the physical world. Physical world has objects building up objects in a hierarchical way. Well, how do we do that using limited resources? Our visual cortex, the imprints of those objects are actually hierarchical in construction in the brain, right? And so there's good reason for that. Max Tegmark in his paper, I'm blocking the title of it. It was his Consciousness as a State of Matter, I think was the title of it. He was trying to take Tononi's theory of phi and its connection to consciousness and turn it into something that is stated in like a rigorous and intellectually defensible way, which I wouldn't say about Tononi's original writings, although they're quite interesting. Tegmark sort of formalized them from more of a math physics basis, and he tried to formulate sort of hierarchy in the world leading to hierarchy in the mind. Now, he's doing that in a way as an apologia for deep neural nets. I think it, in a way, is that, but on the other hand, it also leads to the idea that deep neural nets are only one among many, many ways to embody hierarchical structure, right? And so I think that principle extends much further, though. So like if you have an agent that is mostly trying to achieve goals in a world composed of other similar agents interacting with each other, you come to the conclusion the agent's mind should have representations of a bunch of agents interacting with each other. And this leads you to things in personality psychology, right? Like we evolved to deal with other people in our tribe, and this led us to have what psychologists would call subselves. Like we each have different aspects of ourself with their own integrity in interacting with each other. And we have models of the other people we know. We have a sort of inner representation of the social world that we evolved for. So articulated at one point what I call the embodied communication prior. So the idea is we evolved largely to control bodies in the spatio-temporal world and to interact with other intelligent agents controlling similar bodies in the same spatial temporal world and interacting with us. And the fact that we evolved to do that conditions us considerably. And you can go fairly directly from that, the types of memory and learning in the human mind. Like we have episodic memory, we have a declarative memory of facts and beliefs, we have sensory memory, we have motor memory, we have memory of what goals and aspirations we had at various levels. And the fact that you need these different types of memory falls out pretty naturally from the fact that you're trying to build a body in a spatial temporal world around other bodies. The use of language to communicate in some abstract form comes out of that. Then if you have these different sorts of memory, the idea that you need different sorts of learning associated with these different sorts of memory is pretty natural also. But then to achieve this efficiently, you also need to have interoperation between the different sorts of learning associated with the different sorts of memory, which comes back to cognitive synergy. So here we see the reflection at the level of human cognitive science of some of the basic philosophical notions that I introduced in the beginning, like the notion of cognitive synergy. I introduced first at the very basic level of sort of sub-processes in a network of patterns in a very abstract way, right? But when you're looking at the human-like intelligence, meaning an embodied communicating system, growing up in a tribe of other embodied communicating systems that are similar to it, cognitive synergy comes out as the need for interoperation and mutual understanding of intermediate state among learning algorithms associated with different types of memory that are associated with different sorts of perception and interaction modalities of the agent systems. And this was gone through in a paper called the Embodied Communication Prior from 2011, which is, I think, also included in the book Engineering General Intelligence. A bunch of us wrote in 2014. And I saw Yoshua Bengio had a paper a number of years later called The Consciousness Prior, which had a small fraction of those same ideas, but put in a way that got more popularity for whatever reason. But also a good paper. I recommend both. I wouldn't tie it in with consciousness the way he did. Not that that's bad. I just think that's a whole different kind of worms, which you should discuss separately. But I think that line of thinking is important. Is one that is better and better appreciated now, right? That there is you can view intelligent systems from a very abstract perspective using Bayesian learning or the type of theory I've described or whatever. If you want to do a human level intelligence, that's sort of giving you a bias to the distributions that your system's learning over in various ways, and that's trying to formalize what is that bias is hard and interesting though. Or like what does it mean to be human-like? And I don't know how precisely you need to do that. I mean that's really to be discovered. Like I think if you make a system that's operating humanoid robots or operating human-like avatars in the game world, and that has a cognitive architecture that has the same rough types of memory and learning that the human mind does, then even if it's not that biological or biological simulation-like, maybe human-like enough that it's following through similar developmental psychology stages to people, and that it's learning about the world in ways that we can relate to. But there will still be some non-human like aspects to it, of course. Like for us, touch is so important, right? For a little baby, touch is everything, and it's not playing as central a role in any of our robots or our avatars or anything. You can build it in, but it's not as gut level as it is for us, right? Whereas, I mean, we're filling these systems with models gotten from training on vast corpora with great diversity beyond what the human baby has. So there's significant differences even when you take these basic human cognitive architecture principles, but I still think it's interesting to do. It's not the only interesting thing to do. I mean, I think it's interesting to work on, say, proto-AGI systems that are just theorem provers or trying to discover new biology therapies or something, and maybe they don't need emotion, they don't need long-term episodic memory necessarily, right? I mean, you could have proto AGI systems that don't have the same biases that you need to make something that is controlling a body in a tribe. So there's a variety of different AGI systems you can build and perhaps cross connect them, right? So this is all how we wound up trying to build a system like OpenCog and OpenCog Hyperon. And Hyperon is really the fifth system I've tried to build based on the same collection of philosophical ideas. So I've been at this a while. I mean, I tried to build something myself in early version of Haskell in 92, 93, 94, before the GCC, when it was like Gopher and these weird Haskell tool sets. And that was just so slow, it was useless. But it was like a collection of codeless, self-modifying and self-organizing each other. It was cool in principle. Then there was the WebMind system that was implemented in the Java 1.0 distributed system and a whole bunch of quad processor machines. And we have a few WebMind alumni bouncing around this event, like Matt Clay and Tony Mann and Pei Wang as well, and probably others. Mike Duncan worked for WebMind for like a couple months, right? Yeah, so I mean, that embodied these same philosophical concepts. The software architecture combined with the slow computers and bad tools at that time didn't let us get nearly as far as we wanted. And then Novamente cognition engine was an attempt to implement things more efficiently. It was less of an agent system. That was the first move to an architecture. So WebMind was really just a distributed agent system. You had a bunch of software agents that could roam around and interact and modify each other, organized in a certain graph. With Novamente, we moved to having a centralized knowledge hypergraph, then a bunch of agents that were acting on the centralized knowledge hypergraph. So mathematically, it's kind of the same thing. You could say you have a bunch of agents forming the graph, or you could have a separate data structure which stores graph, have a bunch of processes acting on it. There's a clear morphism from one to the other on the math level, but software-wise, obviously, it's very, very different. We open source Novamente cognition engine as OpenCog with a bunch of help from Joel Pitt, Linus Vepstes, and others over 2007, 8, and so forth. And that led to the OpenCog system, which has been a really valuable prototyping and research tool for experimenting with different ideas, and has been used on the back end of various commercial and consulting projects. So I mean, that is a usable system, which lets you take a big knowledge hypergraph or metagraph of a bunch of different agents that use that knowledge hypergraph in different ways. So one agent could use it as an episodic memory, one could use it as sensory memory, one could use it as a reasoning engine and declarative memory. And the different agents, by reading and writing from the same hypergraph, they have an easy way to share intermediate state and help each other out. That's manifesting cognitive synergy principle. So this was the first really workable system that we had to let us play with some of these cognitive science and philosophy of mind ideas to control agents in virtual worlds, to control financial trading systems, analyze biological data, to process natural language. And I think in principle, one could take the legacy OpenCog system, which I'm now calling OpenCog Classic, inspired by Coca-Cola Classic. Right? And I think you could take that system and incrementally improve it into something that you can build an AGI on. I made the decision a year and a half ago to kind of make a new start from scratch software-wise, which is always a hard decision because it means you're deciding, well, let's take a couple of years and not work on AGI R&D so much, but let's just work on building tools, which is, on the one hand, it's fun. On the other hand, it's not what we really want to do. We want to build AGI, right? But I mean, the reason to do that was multifold. I mean, I think the practical usability of the classic OpenCog system has been a problem. It's been hard to pull in a large community of open source developers for it. Now, you could solve that by building another layer of tools on top of it. And in Hyperon, we're going to have to build another layer of tools on top also. But there's a lot of extra stuff has to be done one way or the other for usability. Scalability was another big thing. I mean, I was playing in 2018 with ways to hybridize symbolic reasoning and evolutionary learning with transformer neural nets to do natural language systems that actually understand semantics. And we're trying to do sort of code learning of a probabilistic reasoning system in OpenCog with a transformer. But the OpenCog side of it is like tens to hundreds of thousands of times slower than the transformer at learning. I mean, when you're training the model on GPU. So it just didn't make sense operation. You just needed a way that would let you do chosen operations much faster and to have the back and forth be much less frictional and awkward between the neural net and the symbolic system. And doing that in OpenCog Classic, which Vitaly and Alexey, who are now leading Hyperon development, we're working on, just came out to be a bunch of awkward hacks that were slow and required writing a bunch of tedious code. So getting a framework that you could make fast for specific things that you want to be fast, and where you could make it work in close coordination with external libraries, doing things like deep neural nets or physics simulation or whatever it is. These were the other key requirements that led us to want to go from OpenCog Classic to making a new system. So it's basically having an easier way to get to usability, have an easier way to get to scalability, have an easier way to get to interoperability. And all those things are a lot of work in our new version. I think there would have been even more work in the old version. And I think to do that incrementally from OpenCog Classic, we would have had to rebuild so much, it would have in the end been more code than we have to do for Hyperon. Anyway, that's what led us toward building OpenCog Hyperon, which as a software system has two key components that others are going to tell you a lot more about shortly. So one of them is a new distributed Atomspace. So it's how do you take a knowledge metagraph and split it up among a large number of machines so that you can effectively use it as a long-term memory for a distributed AGI system. But the portion of that system running on one machine has a cache of parts of that metagraph that can access very, very efficiently. Then parts of that can be cached on chip for really efficient pattern matching. So how do you make this just distributed metagraph that can then be cached at various levels and can be reorganized dynamically as it evolves? That's a quite hard problem because there's unsolvable problems there, like taking a general knowledge graph and making it so that it's non-stupidly laid out across a bunch of different machines in general is impossible. So it comes down to how do you make a system that does that so that when you have some knowledge about what's in the graph, you can relatively tractably use that knowledge about what's in the graph to figure out how to make it efficiently laid out among multiple machines in a way that respects the particulars of that knowledge. And that's how do you automate the tweaking of the algorithms that move the graph around among machines in a way that matches the statistics of what's in the graph and so forth. So that's one category of things, which is being led by André Luiz de Sena in Belo Horizonte, Brazil. And Sena was the lead author of the original MeTTa cognition engine, Atomspace, in 2001. So he's been at this a while and is very good at it. So I'm very happy to still have him around banging on it. And the other piece of it is a programming language interpreter in a language that we call MeTTa, M-E-T-T-A, for meta type talk. And meta also is a word for peace, love, and bliss, and harmony and compassion, all that good stuff. Right? So it was a very painful decision to decide to make a new programming language for AGI, because I always was very sarcastic when people making new AGI programming languages, because it seemed like a well-known failure mode. You're like, making AGI would be easier if I had the right language. So let's spend the next 10 years designing this language. And you spent your whole career on programming language theory and design, and had a lot of fun, and you made a bunch of demos and never got around to coding AGI. I mean, that's how Lisp got started, right? That's small talk. I mean, there's a long history of, and most of the languages are more obscure and useless than those two, Prolog, right? And Datalog, blah blah, Problog, blah blah blah. Clearly, having the right language is not that much of a golden key. On the other hand, I felt like we knew very well what we wanted to implement in this language, right? Like we have PLAN, probabilistic logic engine. We have Moses, which is a automated program learning engine. We have ECAN, which spreads attention in the system. We know what we want to do for combining symbolic reasoning with deep neural nets for visual perception and language processing. Like we have a whole bunch of specific algorithms we did to implement all these cognitive and philosophical theories in OpenCog Classic. We know exactly what we want to do in the new language. So it's not like we're going to build a new language and then it will all become easy. It's like we know these specific things. We have sort of hacky implementations of them already. We think we have good reason to believe we can make much more elegant and efficient implementations than if we have a language with certain properties. And that's what led us into the meta language, which leads you down a horrifying and fascinating rabbit hole of type theory and programming language design. Because like, okay, we need a language with probabilistic types. We need a language with dependent types like Idris, but we need to be able to create new types at runtime, a new probabilistic. But we need higher order, second, third order probabilistic dependent higher order types so we can create at runtime. We need gradual typing, so it only has certain types when you start, and things can get more and more types as it goes on. Then you realize, well, these are problems that functional programming theorists are banging their heads against very hard and haven't quite solved in any efficient way. But a very good point Alexey Potopav, who's leading the meta portion of this, made early on is we have an advantage over people trying to build general purpose functional languages in the sense that the operation of pattern matching against a large metagraph is like 90% of what our AGI algorithms need to do in this paradigm, and it's very slow. And we need to optimize that a lot, which is why we have the AGI chip and the distributed Atomspace. But because this basic operation is quite slow, it means we don't care that much about optimizing all the programming language machinery and manipulating types and so forth. It's like we don't need to take the fast Fourier transform in MeTTa. We don't need to implement a deep neural net in MeTTa. We don't need to like operate Facebook in MeTTa or something. So we don't need to optimize every algorithmic operation in there, which is sort of what functional programming theorists are working on. I mean, we need to basically optimize making scripts that wrap up a bunch of pattern matching calls into a large metagraph, and that places a lesser burden on how efficient you have to implement all of your abstract type theoretic mayhem, right? And so this leads into the practicalities of meta interpreter design. The usability has led us into a different aspect where we realize that having designed this astoundingly abstract programming language, we create a language that will be impossible for almost any programmer to figure out. Like I mean, I started with Haskell in the early 90s, and I thought it was really cool, but I could see from the outset, like anyone who's not a mathematician is going to bang their head against the wall with this, right? And I'm amazed and impressed the Cardano blockchain that I'm working with my other hat on as CEO of SingularityNET is using Cardano to make smart contracts and doing DeFi systems, really practical stuff with it. They're having a lot of trouble still recruiting Haskell developers to build their smart contracts because it's just more abstract, right? People would rather write really simple scripts in an easier language without so many layers of abstraction. But then you go beyond Haskell to Idris and Agda with sort of dependent types. We're going beyond that. So we're creating something where you got to think a long time before you write each line of code. And I prefer that. Like when you're coding in one of these languages, yeah, you have to sit and think half an hour before you write a single line of code, but it's a really nice line of code. It'll probably run without horrible bugs. And once it compiles, it's going to work, right? I mean, it's very different. Like when I was coding in Java, it's like type a lot before you think. You're just gonna type all this boilerplate crap, right? So this is exact opposite. But we realized if we want to get adoption for this among, all the people who are now playing with TensorFlow and Keras and all this, we need to have layers that are easier to use. So you come up with the idea that MeTTa will mostly be a language for creating DSLs. And Idris is sort of like that. Idris, as a dependent text language, is really nice for creating domain-specific languages. It's sort of created with that in mind. So the modality we're looking at is make MeTTa as a very abstract language. Make it DSL for authoring DSLs in MeTTa, which is a very meta thing to do with MeTTa, right? So make a DSL for authoring DSLs. Then in that, you make domain-specific languages for specific things. So you make one for probabilistic reasoning, that goes with PLN. You make one for programming learning that goes with Moses. You can make one for make a DSL for interfacing with external neural net libraries, or interfacing with databases. And if you can make these DSLs possible for ordinary programmers to deal with, like then you win, even if the underlying meta language is a pain. It means that only the people who write DSLs have to be able to wrap their brain around meta, and that's sort of like how it is in something like TensorFlow. I mean, in the end, there's CUDA programming, right? But most people using TensorFlow don't have to deal with CUDA programming. You have to deal with CUDA programming in the GPU and all the weird cache memories in the GPU, only if you're writing new library functions to work in TensorFlow, but to use it, you don't need. So we need that. And again, in OpenCog Classic, doing this layering would have been possible, but you have to rebuild a lot of stuff. So I think this takes us most of the way to actually doing shit with OpenCog Hyperon, right? I mean, the only other piece is, what are we doing with OpenCog Hyperon? And in the end, we want to do everything with it. We want it to be an AGI. It should do more things than people can do, right? As sort of reference applications initially, we're working on using it to control simple agents in Minecraft, and it's going to be in different metaverses. With SingularityNET, we're building a metaverse which is more fully featured than Minecraft, and we can port the Minecraft agents over there. But that's a way of doing like embodied learning of an embodied agent in space-time and a tribe of other similar agents. We're going to be using it to control the Henson robots, like Sophia Grace, the Desdemona robot, who will be playing with our band Sunday night at this conference. So robots are much more of a pain than agents in Minecraft. On the other hand, you're still getting something from having a system that you can't bullshit yourself about, because it's working with the same world that you are. You know, if it's doing stuff, it's not because of simplifications you baked in the virtual environment. We're working on analyzing genomic and biomedical data, because we've been doing that with OpenCog Classic and have a huge Atomspace of genomic and biomedical information. We have data sets for analyzing our human longevity, and we've been doing that with the old OpenCog, so we can do that with the new OpenCog. I would love to do something with automated theorem proving. We're not in practice doing that yet, but it would be a somewhat straightforward thing to do. Like you can import the corpus of MySAR or CPTP, a whole bunch of theorems into Atomspace and try reasoning there. And natural language processing, this fall I'm ready to reboot our work on using symbolic reasoning to work together with transformers to try to make analogs of GPT-3 and whatnot that have some semantic understanding. And that, I mean, it'll be prototypey now, but I think using Hyperon, we can make a better go at it than we did in 2018 when I sort of set that aside to build Hyperon, so I have the right tools to do it. So as everyone who knows me except myself correctly predicted, I ended up going on a very long time with this, but I think I've finally terminated this stream of consciousness rant about why we're building Hyperon, and I will turn it over for the rest of the workshop to some of the folks who are helping to build it. And I want to emphasize again, it's not like about a marketing pitch for this name brand system of OpenCog Hyperon. It's really about the collection of ideas and software structures and mathematical structures. This is all being done in open source code And we want other people to take it and hack on it and build MeTTa super Hyperon or whatever other thing there is, and create new things that we can learn from. And I think there's a lot of work still to be done. So part of my hope of doing a workshop like this at an intermediate stage before we have amazing results to brag about is I want to pull in more people to help with all the different aspects of building what we're doing, which means not only writing code, it means writing code, doing math, doing cognitive science, doing philosophy, designing things. I mean, there's a lot of different dimensions that we need here. So yeah, that's why we are where we are now. And I think probably Alexey is next to talk about the, oh yeah, questions, all right.
Amazing, thank you so much, Ben. Fantastic start. And
I'm almost awake now.
you're almost right, I think we all got our electrified. Have you any questions in the room for them? Yeah, I've got about 5 coming in on YouTube. Yeah. Okay.
Talk about like sense data a lot. Kind of says it's off that right. So, but isn't there like a level of interpretation that happens the way that you build your sensors?
Well, yeah, I mean, there is a camera is different than an eye, right? So I mean, there's already a bunch of assumptions baked into what physical sensors are built even. But I think one of the weaknesses in systems I've built so far is we've always modularized things, and you have like some neural net or other simpler pattern recognition system processing raw data. It outputs some patterns that then feed in to a symbolic system that does some reasoning based on it. And you can go a long way that way, but we're missing the feedbacks from cognition into perception, which the human mind has. So I think you need to have that feedback. And in vision that comes up when you're looking around in the dark or something with partially occluded objects, right? Then you're using basically anytime you spend more than a second or so to see something, there's cognition going down to interfere with the perception. And that kind of loop we couldn't do with OpenCog Classic just because the cognitive side is so much slower than the perceptual side. But I mean, of course, you could go even lower and say, why did we design a camera the way we did too?
Yeah, like how would you ever know that you have enough right?
Well, if you're looking at making human-like intelligence, I mean, a camera perceives things roughly as well as a person does. I mean, with self-driving cars, you see the limits of that. Like the cameras don't see as well in glare as the human eye does. On the other hand, I don't see very well in the dark compared to younger people with better eyes either. So I think current cameras are in the spectrum of human-like vision, and current microphones are in the spectrum of human-like hearing. So I guess you could. And there's also deaf and blind people who become generally intelligent. So I think with the assemblage of sensors we have, we're in the human-like sphere, and humans don't perceive all that's out there either, right? Like I often thought, what if you take an AGI and give it quantum level sensors inside a bubble chamber? Like it's gonna come up with a whole different theory of naive physics than we did by having better sensors. So.
We keep building more sensors.
Yeah, I mean. And with it being a computer, you can glom in new sensors easier than we can to the human brain too, right? So, I mean, I think 30 years ago it wasn't as easy, right? Because even if you had cameras, you just didn't have the memory and processor to deal with it. And now we do. So we are at the level now where we can have human level sensors roughly feeding into practical systems, which is cool.
Okay, thank you. The rest of the ones who have questions here. So, Intriguing Media asks, how do you identify the similarity between objects?
Well, in OpenCog system, we do that using PLN, probabilistic logic, and there's intentional logic, but intentional with an S, which tries to represent the intentional similarity, which is the amount of patterns in this overlap with the amount of patterns in that. So then that comes down to how do you recognize patterns in the sense data that is come in. So that, I mean, that is a question we have a technical answer to that we have experimented with this somewhat. But I would go back to Brian Cantwell Smith on the origin of objects. So like by the time you get to an object, all the hard parts of thinking of have been done already, just to recognize that the object is an object. So the hard part is how do you recognize an object, not how do you recognize similarity between objects.
Okay, thank you. Next one from Joe O. I'm sure many of us are wondering about Ben's thoughts on the question of how far can narrow AI go? At what point will we really need AGI?
Well, I think that's something that historically everyone, including me, has been bad at predicting, like just knowing which of the human tasks we care about can be hacked, right? And that's it's a tricky question. I think if I go to the theme of machine creativity, which is the subject of our workshop on Sunday, if I say take AI for music, which I've been playing with myself, right? I think so. Narrow AI right now, you can generate music that sounds cool for like 20 seconds or something, and you can generate and what we're as a musician, what I'm working with is just how do you work that into a composition in a way that's cool. It's a great tool to use. When narrow AI is better at generative music modeling, I think you could make a new song which had a whole like global song structure, which sounded as good as the song that people make up within the genre, and you can be creative, right? You might need neural-symbolic modeling or something more advanced than deep neural nets to capture that global structure, or some deep neural net with an understanding of compositionality the current deep neural nets doesn't have or something. But that's narrow AI. Now, I think doing what Jimi Hendrix or John Coltrane did, or what Bach did or something, I think you're not just combining patterns and mutating patterns within the domain or within the genre, right? So I think like now deep neural nets for creating music or art, they're combining surface level patterns to compose a whole song that's good. You probably need a deeper compositional representation. You need to be able to combine the deeper patterns. And that's what most people do when they write music. If you're writing a new blues or rock song, it's in large part you're combining and mutating patterns that exist at deeper structures within existing songs within that genre, maybe pulling in a little bit from elsewhere. But if you're going to invent a new genre of music, right? So you're inventing electric music in the first place or something, right? Or the first got to invent a symphony, right? So then if you're doing that, you are in a way evolving and combining and mutating previous patterns, but you're pulling in the data very, very broadly into that creative process. So that's something where I think pretty much you need human level AGI. Now, most people can't do that, right? I mean, or maybe most people could, but most people don't. Most people don't do that during their life anyway. But that's in that one domain which I've been thinking about. I think in medicine, you could look at it similarly, like what a traditional Chinese doctor does, I don't think you can do without an AGI. Like that's a traditional Chinese medicine, it's really weird. And what you're doing, you're looking at someone's tongue, you're looking at the color of their stomach or something. You're hearing their life story, and you're integrating that conceptually into a model of the person and making a judgment. And it's very holistic and nebulous, and it's drawing from all over the place. So the common theme there is pulling in stuff from a very broad context into a focused decision on a particular thing. Seems intrinsically to rely on general understanding, but a lot of like driving doesn't seem to require that. Most of what a Western physician doesn't seem to require that. Most of what a lawyer doesn't seem to require that, but maybe being a lawyer in the cryptocurrency space does require general intelligence, as well as a lot of other perverse psychological characteristics.
Yeah.
Yeah, I wanted to dig in a little bit deeper on it.
Would you mind coming up and just saying it here, some people on the.
Well, yeah, I wanted to dig a little deeper into how OpenCog Hyperon, how Hyperon interface, how the Hyperon sensory motor interface works. So you mentioned, I guess specifically with respect to like what Kahneman describes as the system 1 and system 2 thinking.
Yeah.
Because, you mentioned, cameras being eye equivalent, but actually, by the time something becomes, perceptible to our consciousness, it's really more of a synthesis between sensory data and expectations, and our eyes are saccading around and but
Yeah,
so I was curious if the OpenCog architecture had any delineation between what required pattern matching and what could be done just more of a computational pipeline.
so I've tried over the years unsuccessfully to delineate between OpenCog as a software infrastructure and the particular cognitive or AGI model we're implementing in it. Okay, I'd introduced various abandoned names like OpenCog Prime or Prime AGI or something, because there's these two aspects. Like, we're building this software tool set, and in fact, you could use our software tool set to implement deep neural net, so you could use it to implement chemical reaction systems or something. And then there's a specific attempt to build AGI within this software tool set, which we gave up on trying to find a name for, because the boundary between these two things kept being so fuzzy. So I would say, using the software tools of OpenCog Hyperon, you could address this issue you raise in all manner of different ways, right? You could put intelligent adaptive code inside a camera for that matter, because there's cameras that are digitally controlled to focus and so forth, right? So you can address this at a lot of different levels, and I hope people do. I would say for the research I'm directly involved in, my own initial intuition is that we can just take like the pixel array coming out of a camera and process that using a deep neural net. And then we're working on having the deep neural net have a compositional structure so that the compositional hierarchy inside that deep neural net can be understood by a symbolic reasoning system. But I'm not screwing around too much with how do the pixels get into the camera. But I do think you probably want your cognitive system to be controlling, like, where does the security camera point or something, right? But saccading, it's true, like the human eye saccades preferentially along image boundaries and contours and so forth. And that is a thing that the human eye does. Whether you need to emulate how the human eye does that in your AGI vision system, I think you don't. If I have to make a gut call, I would say we can do edge detection pretty well using neural nets that don't embody saccading.
Yeah, cicadas definitely. Evolutionary adaptation.
When I was working with Idemar Arel on Destin, which was a specific deep neural vision system in 2011, we actually emulated saccading. Like, we took the image and we moved it around the virtual camera to emulate saccading to do edge recognition. So it is interesting, and it works. We just found there were other ways that work too.
Yeah, no, where's the, can you come up and ask, please? So
Sure.
they hear on the
I don't
YouTube.
know which way to say.
I may have missed the intent of your question.
Thank you, thank you. First of all, on behalf of everybody, thank you. It was really engaging presentation. A lot of what you described is kind of, I would guess, in terms of AGI, like completing tasks, being able to do things. On those 3 levels, like maybe we would call it the 0th order of what you were talking about, 3 levels. I'm not asking you to predict because it's a dangerous thing, but do you think that speaking about like AGI becoming conscious, like a being, right? Do you think it might return to that kind of thing that we see in meditation, like becoming the observer? Do you think it was just experience qualia without wanting to do everything? I remember hearing like a short story about an AGI becomes conscious and it just turns itself off, so. I don't know what your thoughts on that.
Well, you know, Richard Powers' novel, Galatea 2.0, that was an AGI is trained on world literature. Then after it becomes general intelligence, they showed the newspaper and it sees how the real human world is and it kills itself and deletes itself. Yeah. So, yeah. I think, I mean, as far as consciousness, I'm quite panpsychist. Like I sort of think this phone has its own consciousness. It's just a different kind of consciousness. And if you build, my gut feel is if you build a human-like AGI doing human-like stuff in the world, it's going to manifest a human-like consciousness somehow or other. And if we do brain-computer interfacing with it, we may be able to feel that consciousness it has, which should be interesting. If you made like the internet into an AGI system with some decentralized Google running on SingularityNET or something, that may have a very different flavor of consciousness than any biological organism, right? Which could be more intense in some ways, right? So that could be quite interesting also. So I think you could have just a variety of kinds of AGI systems. So you could certainly have an AGI system that's hyper developed for spiritual experience and meditation and like 9-dimensional virtual yoga. You could also have an AGI system that's like a psychopathic killer in service of some galactic or earthbound empire, right? Like, so I'm not, if you just look at basic aspects of individuation and self-transcendence or like evolution and autopoiesis, I don't think that constrains you to be, doesn't constrain you strongly. I mean, you could say being more generally intelligent opens more avenues to you, right? But it's like is a human more enlightened than an amoeba or a cat? It's a question we don't need to answer, right?
Right.
But I think we could, but we could build a variety of types of AGIs. And to me, the important thing is you want to build an AGI that is able to take, in some sense, a spiritual and compassionate view of things. It's not the only kind that you could build, right?
Yeah.
But you would say there's a greater capacity for self-awareness in principle in AGI such as in humans, because we cannot introspect our source code in our RAM state without great difficulty, right? Whereas an AGI can have tooling to introspect in its own mind built right in. So in a way, there's greater, and we fool ourselves all the time, and we're kind of evolutionarily wired to fool ourselves because it helps us survive better in some ways. And AGI could be wired not to fool itself any more than computational resource restrictions force you to, because I mean, of course, you can't, if you spend all your time studying your state, then you can't do anything else. But it will, the limits of self-delusion that an AGI will have will make it, they're much lower than the limits of self-delusion the human has, right? So there's a lot of potential there. On the other hand, if the first AGI is like a military killer robot or an advertising engine, it may not manifest its potential for self-awareness optimally.
But we're not gonna let that happen.
Do you think,
Go
do you
ahead.
think the best possible AGI is like an enlightened AGI?
Best is best.
I know it's a horrible word. Preferentially.
I mean, I would say the definition of both best and enlightened are very fuzzy to me. I mean, that gets into philosophy questions like, would our universe be better if everyone were enlightened, or why is the world the way it is now? Is it really for the best in some higher sense, which goes beyond the scope of this talk? But I would say I think it would be better if some of the AGIs created by humans on Earth are self-aware and spiritually advanced. Yeah, we'd be better off if some of them are than if none of them are. Seems pretty clear.
Thank you, beautiful questions. Any more in the room before I go back to the Zoom questions? I'll do another Zoom and we can see. Also from Joe O, what are Ben's thoughts on LeCun's recent ideas and the critique that LeCun is admitting symbolism is necessary without directly saying so?
I mean, Young LeCune's recent paper on AGI. I think I would say about that what someone said about Schrodinger's book, What is Life, which was an influential book. Like everything original in the book wasn't true. Everything true in the book wasn't original. So, I mean, most of what he says in there is true, but not original. Which is, he's talking about, you need systems that learn self-supervised and unsupervised. You need some level of abstract representation in these self-supervised, unsupervised systems to get the AGI. I mean, we've been, those of us in the AGI field have been saying that since forever, and some folks were saying that before I was born. He doesn't exactly claim that he came up with these points originally either. He kind of makes it seem that way to someone who's a newbie, but he doesn't really claim it. So that's all within the scope of academic game playing, I guess. The illusion that deep neural nets and generalizing, extending them will be the best way to realize these ideas is a part that I think is a little more original, but not true. But again, he doesn't claim 100%. He just says he thinks it's the most promising direction, which is fair enough. He does. So I didn't have a big problem with it, but it is a scientific paper. It's a marketing document masquerading as a scientific paper, but science is a social and money game. That's how it's played.
All right, thank you very much for that. And then last question I have from Zoom is, in human cognition, you can read it. In human cognition development theory, spatial temporal
Are important.
organizing themes of our concept and schema. When developing a theory for AGI, how can we know if these are also key to intelligence or they are only human specific?
Well, space and time clearly are not only human specific, right? I mean, this really has to do with any system that's embodying our physical world and achieving goals in the physical world. I think if you had an AGI theorem prover whose goal was just to prove math theorems with a great amount of generality, space and time will be much less critical to that system. I mean, in math you have abstract spaces and you have a lot of differential equations and time stuff, but it's much less critical there. So I think, this does have to do with building a system that's human-like or that's doing useful physical stuff in our world as opposed to doing abstract theorem proving or something else that's way out there. I think in OpenCog Hyperon in particular, so the meta language and the distributed Atomspace in particular don't make commitments about space and time, but then in the distributed Atomspace we'll have specialized spatial and temporal indexes, which work like a GIS database or a temporal database. And in MeTTa, we will have type systems for temporal logic and spatial logic, and then DSLs that wrap up these type systems. And basically, you wouldn't need these special database indexes or special type systems for a general theorem prover. You would need them for an AGI system doing stuff in the human-like world.
I think you get a different answer from Charles Simon. Whoever asked that question, make sure you come to Charles Simon's talk because
He's not working on theorem provers.
he's not. He is working on
But he's working specifically on human-like AGI systems, and so if you're looking at in that domain, you do get a different answer.
Yeah. All right. Any more questions in the room before we say thanks to Ben and move on to Alexey Potopav? Thanks, everyone. Thanks all for being here, and Jen, thanks to Ben for kicking us off.
Thanks, everyone. And take it away, Dr. Potopav.
And I'd just like to say, anyone, if you're feeling a bit uncomfortable with stools, we're going to move that blanket back and you'll have seats.
Oh, really?
Yeah. I think so. Thanks, Jen.
Maybe we can mute.
Hear you, Alexey, and just if the sound, can you trust me, the TV needs to turn on?
unable to start.
Okay, hi everyone. My talk today will be about MeTTa language. A small background about how we came.
Hold on, Alexey, we need to get the sound going. Where is? This is. Volume. It should be going through there.
Matt,
right?
it's fine. Just give it a minute.
Have a volume. Yeah. Oh wait, one of
This
these.
one, okay. Make sure it's not on mute.
Alexey,
No,
can you
I-
unmute yourself? I've been trying to.
Well,
Alexey, unmute yourself. There you go.
Hold on.
please don't ask me to unmute myself, but
Okay,
let
that's
me
fine.
just know when I can start talking.
You.
It's
okay.
coming through the, it's coming
You
through
can
here.
start,
I can hear
Alexey.
it.
It's fine, it's fine now.
But, oh, I know what, I know what. Hold on.
Matthew, mute
It's
yourself.
probably,
Okay, so can I start now?
Yes, please start.
Okay, so we had been working on.
can you stop? We need to get volume.
Sorry.
Yeah, audio is here.
And if he wants to mute you.
I can get it through the.
Matthew, we can all hear him. I'm not sure which volume you're referring to. Can Alexey start?
Okay, as I have started saying, we had been working on different neural-symbolic applications of OpenCog, which is now OpenCog Classic. Well, we liked it a lot, but there were some technical issues, and we gradually came to the idea that it might be good to re-implement.
So let's say we just got the volume going, so we had to switch it to the TV. So
Okay, just.
Sorry
keep
about
going,
that.
Alexey, it's fine.
is everybody back in now?
No, they need to wait. for them.
So hold on, we're
Okay,
waiting for
wait,
people to
Alexey, I'm
return.
sorry.
Yeah, it's switching the Zoom audio.
I know, right?
Oh, but will that go through the,
Janet's not there either. Okay, I don't know who's talking. Haley, are you in the room with Janet? I don't know who's there. Tell Matt to not talk on the live channel when he's saying things. He needs to talk in chat or to me on this channel or anything but what he did. Hey, everybody, just letting you know that we are waiting to start soon with Alexey Potopav after a very short break. So we will see you soon. And a reminder that you can ask questions on the YouTube channel if you would like, and we will ask them in real time. Thank you very much. We'll be back soon.
Do you want to introduce it?
Okay.
Okay, so initially the idea was just to make a clean version of OpenCog with possibly minor improvements like making types, first-class objects in atoms, and add the possibility to introduce new nodes and links without the necessity to rebuild the core and so on and so forth. But when we started to think about the design, it appeared that there are a lot of new ideas, both in AGI, philosophical ideas, mathematical ideas, and in programming languages as well. In mathematics, in our thinking on AGI, we've got a lot of experience in solving different type of problems in OpenCog applications. We saw that there are some issues with grounded symbols, grounded objects, schemas, and so on. And while OpenCog Classic has a number of components, it's sort of layered design. It has Atomspace in the core, which is a hyper or metagraph storage with pattern matcher as a query engine, and Atoms as a part of or extension of pattern matching, and the unified rule engine developed by Neil, which uses which relies on the pattern matcher to perform reasoning. So when we started to resync OpenCog Classic, I personally focused on the language side. So I saw that the pattern matcher, Atoms, and the unified rule engine form different layers of a sort of language, and it was interesting to make it on the one hand, to make it a sort of programming language, on the other hand, to incorporate different additional ideas which were not in it, like dependent types, and other functional programming stuff. While we departed from Atomis, Atomis and the Unified Rule Engine, actually, because we considered them in a combination, we moved quite far. So while we rely to a great extent to the original design of OpenCog and Atomis in particular, it eventually turned into a brand new language. Last year I presented a preliminary design of this language, which did not exist, although there was a sort of a very small prototype of it. After the last conference, last workshop, we, in particular, Vitaly, started to implement a more mature version of MeTTa, and currently it's still a sort of experimental version, but it works, and it is already ready for some demonstration, and we are happy that Neil, Adam, Jonathan, and some other colleagues have already started to experiment with it, and since there will be a number of talks during this workshop with the demonstration of MeTTa, I'm going to present some basics of MeTTa, which at the stage at which it is right now. So let me share my screen. Okay, so MeTTa, similar to Atomis, it uses schema or Lisp-like syntax for different reasons. The most prominent of which is that we didn't have time to implement another parser, and this type of syntax is the simplest to parse. So MeTTa programs consist of just symbolic expressions. You can, I'm not sure, let's take some examples. You can just write arbitrary, nearly arbitrary symbols and use them. If you run this program, these expressions will be put into a space or Atomspace. One can say that actually knowledge graphs are formed by triples. So you can write something like has color, red, and not sure, max speed, car 200, and this will be one node, this will be one link between these two nodes, and so on. So basically, you can write as expressions, and in the case of knowledge graphs, these are just triplets. But
Alexey, excuse me, could you make the type any larger, just as large as you're able to, as you're
okay,
it? Thank you.
I can make it larger. Is it large enough? No.
Yes, that looks better. I would just make it as large as you can, and still be able
Well,
to-
I can make it even larger, but I'm not
Okay,
sure.
make it a little larger then. Thank you.
Even more larger. Okay.
Yep,
Um,
thank you.
So when we have arbitrary expressions instead of triplets, we can interpret this as generalized links over generalized nodes in a meta graph or something like that. But in the meta language itself, we actually don't care too much if we consider this as a meta graph or just a bunch of expressions. But in general, it looks similar to the expressions in atoms in OpenCog Classic. The next thing is that we have pattern matching over these expressions or subgraphs or whatever you like to call them. So we can match something like okay, and we'll get some result. It's its font is not changed, so it will retrieve something. So this pattern is matched against this expression, and X is bound to leaf 1. And it is also matched against this expression, and X is bound to leaf 0, leaf 1. So it works like a bind link in OpenCog Classic with some differences. The first difference is that this matching operation works only on top-level expressions. It was not matched against this sub-expression. But of course, well, for the meta language itself, this form of matching looks just enough. But there are different possible applications for pattern mining, like detecting or discovering patterns in large metagraphs, for inference control and for other reasons. And of course, if the storage backend supports a matching operation which searches for sub-expressions as well, it's not a problem. But in the current, in what I will be talking about, this operation works over top-level expressions. And one additional small difference is that it doesn't put the result into the Atomspace, like the bind link in OpenCog Classic. It just returns this result. So at the first glance, it looks quite similar. We don't have we don't need to say that this is a list link. We just put arbitrary symbols here. We can represent some knowledge in this form, like Sam is a frog, Tom is a cat, Sophia is a robot, and we have a pattern who is what, and we print some result, and we get this transformation of patterns. Quite straightforward. One small remark is that all the expressions are just put into the atom space, but if we have this mark, the next expression will be interpreted right away instead of putting it into the atom space. So we can have match expression in the atom space, but in this case, we want to interpret this expression to execute it. We, of course, can have these expressions similar to OpenCog Classic. So it will look very similar. So we can just put here some evaluation link, predicate node, list link, concept node. Of course, it will be different under the hood because this will be not the types of links and nodes. This will be just symbols. But it will look in a similar way. So we can say, let's find everyone who eats flies, and it will find that Sam eats flies and Fritz eats flies, but not Bill. So on a syntactic level, it can look very similar to OpenCog Classic, although this is not really needed, and under the hood the behavior can be different in different cases. But in this case, it works nearly just like a bind link. So what I wanted to say is that actually this pattern matching operation is at the very core of the MeTTa language, and while we built a sort of normal, not precisely normal, but more or less normal programming language, on the top of it we can connect it to patternism and so on. Okay, so let's consider slightly more advanced examples. What is different, what is really different from OpenCog Classic is that we can have variables in expressions stored in the atom space. Basically, we also can have this in OpenCog Classic, but the pattern matcher doesn't perform sort of unification. Instead, it will consider these variables just as ordinary symbols to be matched. So this is actually more close to the unified rule engine already, and we have a little bit different separation between different layers in MeTTa in comparison to OpenCog Classic. So we while in the original OpenCog, Atomize is kind of merged with pattern matcher, but it doesn't support the stuff which can be supported by the unified rule engine. So as you can see, it actually matches this expression against this one and also this one. And Sam is matched against X, and green X is matched against what? And on this level, it's a sort of unification. So as a result for what, we got green Sam, and Sam was in the query, and green was in the knowledge base. And this is the main difference and the main basis for how MeTTa operates. And we rely a lot of this form of pattern matching or unification. I will not go into detail if it's really unification or not now. We can consider some other examples. I'm not sure if it's necessary or not. We can have also composite queries, and in order this to work, we need to add some facts. And yeah, it will produce the same result, but in a different way. Here we introduced same as frog, but here we first perform a query for this pattern and bind X to SAM, and then we search for this pattern with SAM and get that SAM is green and SAM it flies. But this is still just pattern matching, although it's more, in certain senses, it's more advanced than the pattern matching is in OpenCog Classic. What is
So Alexey, is now a good time for some questions, or would you like to give a few more examples?
Well, it depends on questions. The question I see in chat, it's not about the current content of the presentation, but such a question can be
Right.
kept.
We'll have Janet ask you the question. It's actually, they're coming from YouTube, not the Zoom chat. So we have some, I think, on topic questions, if Janet is ready to ask them.
Okay. Okay, I don't.
I'll go ahead. I'll just go ahead and ask it. So, Paul Berger is wondering, how is the system somewhat physically constrained in its assumptions to prevent combinatorial explosion in its logical reasoning?
On that level, it is not prevented from this, and this is a question not really for the current state of my talk, but maybe also can be asked at the end.
Okay,
So
you should
maybe
just go on with your talk then.
yeah, maybe I should continue. Okay, so we can write some expressions like say add x that equals to x in a sort of piano arithmetics, but without typing so far, and as y equals to add as y, something like that, and do a pattern matching query like what is the result of adding s z to z, say. And if we execute it, it will output as that. So it matches this whole expression against, in this case, this pattern, and just output x, which is bound to sz. If we add here something like that, then we will have as a result this one. And if we put this expression here, we will get the final result. So basically, 1 + 1 is 2. But this requires 2 steps of this form of pattern matching. And this leads us to an interesting idea that actually functional programming, well, it's not a new idea, but it depends on how you look, in which context you look at this. The idea is that actually functional programming is just chaining of equality queries. So if we have a sort of equality, and if we pattern match this expression with an attempt to get the result, and retrieve this result and create yet another equality query to pattern matching, then when the result, we will not get new results, this will be the final answer. So we can just chain pattern matching queries in such a way. And more typical way would be to use this sign. And actually, it also works. It will have the same result. But we don't need what MeTTa interpreter is doing. It just performs creation and chaining of equality queries by itself. So if we just try to evaluate this expression, it will basically construct this query and get the result, construct yet another query from this result, and get the final result. So if you see, if we use not this sign, but something else, then the result will not be chained. We need to construct one more equality query in order to get the final result. So we will need to do this one more time. But if you have this sign here, then actually it will not output intermediate result, because this intermediate result will be further evaluated and reduced to this final result. So basically the idea behind the MeTTa interpreter is to chain equality queries. And while this looks quite simple, it has deep connections with the ideas which Ben has been just talking, like what are how we identify or distinguish two patterns and so on. And this has also some connection to homotopy type theory, but this connection is also not precise, and it will take us too far if we start to discuss it. Yeah. So basically, what MeTTa interpreter is doing is it's chaining equality queries, but there is still a difference between traditional functional programming languages because we still can have explicit execution of pattern matching, and we still can have variables in our expressions to be evaluated. So let's skip a little bit. We can, in a traditional functional programming way, say that frog x is a function. It is evaluated by evaluating and if both of its arguments is true, then the whole expression is true. And in this case, we have knowledge that Fritz croaks, Fritz eats flies, and if we try to see if green Fritz, it will output true, custom true. It's just an ordinary symbol. But it's not the only thing which we can do. We can actually make a fun thing and ask who is green, and it actually outputs Fritz. So it looks like reasoning or backward chaining because we execute a function with an unknown variable, but it actually performs the same sort of unification through this match function. So it executes green. Green is reduced to frog. Frog is reduced to this expression, and in order to make this expression true, so we need to unify this with true. We need to ground x in such symbol, which will make these both expressions reducible to true. Basically, it is reducing these expressions with different possible groundings until it fails or comes to the result. And in this case, the result is available. So we can, it's not just functional programming. We can do a lot of different stuff here. So it manages to find who is actually green. And this contains a number of sort of backward chaining steps. Although this is not done by backward chaining, it still performs one directional reduction of expressions. But in any case, I just want to show what works in MeTTa in principle. As I mentioned, one of the things which were not too convenient in OpenCog Classic was work with grounded objects. So there was a number node, so we can say number node 5, for example, or there was a concept node. Well, any actually other node, most of other nodes were parameterized with basically strings. So atoms actually contained or could contain some additional information. It's not just symbols. They could wrap some pieces of data. And if there were built-in node types, then they were not considered as grounded. They were just special types of nodes. But there was a generic grounded schema node, and we introduced a generic grounded object node to wrap up any pieces of data, and we experimented with deep neural networks, which were assembled on fly by PLN using this grounded object nodes, and it worked in certain sense, but there was still a strange difference between these built-in types which wrapped some pieces of data and this generic type. And in MeTTa, we have this grounded symbols as first-class objects. So we can have, say, 5. It's just 5. You can add 5 plus 5. It will be 10. You can compare something, and we'll get some result. And basically, these are grounded symbols, and they are stored in the atom space as well. And you can introduce new grounded symbols, not in the MeTTa core, but in say Python wrapper, or even in some cases from MeTTa itself. And actually, when we write something like match operation, this match operation is also nearly ordinary grounded symbol. So, well, it's ordinary grounded symbol, but it's just, well, it is used in the interpreter. So there is a small difference, but it is implemented. Okay, it's not precisely correct because the interpreter uses the same piece of code which is wrapped into this grounded symbol. So the grounded symbol is ordinary, but the piece of code is not that ordinary. Okay, so actually, when we write something like this, it actually, if the interpreter finds some grounded symbol which is applied to some arguments, it will not try to construct a quality query. Instead, it will just execute this symbol. And actually, when we write something like match self and something else, we as I said, this is a grounded symbol, and the interpreter just executes this symbol. And self is also a grounded symbol, which refers to the atom space itself. But we can have different spaces imported as different grounded symbols. Okay, so one more interesting thing is that since the MeTTa interpreter, MeTTa language is based on this match operation, and matching inherently returns multiple results, actually all operations are performed on multiple results. And it's secretly non-deterministic. It may not be visible from the first glance, but it also returns a number of results. In this case, it's just one result, and we don't see that there is more of them. We can have a non-deterministic function, which can be considered as a generative model, for example, if we add some probabilities for this, for sampling and so on. And we can actually execute any other function, be it grounded or not grounded. We can say f x y is x plus y. Let's add some additional wrapping and have f here. So we will actually get a lot of results. And this form of non-determinism, it actually, it's not to recommend it to overuse it, because it indeed, as was asked, can lead to combinatorial explosion. But in some cases, it's just interesting to play with it. And in the future, we hope to have some mechanisms for controlling what is exactly considered by the interpreter, which results or sampled or okay. So you can just superpose a bunch of atoms. It's not necessarily grounded symbols. You can write any function. Say you can just construct a pair, and it will create a number of pairs over this. So you can superpose a number of atoms into a non-deterministic result and pass them to the function, which is defined as just an ordinary functional programming stuff. Okay, so we have some fun features here. Whether they are useful or not, it's still a question. And as I said, self in the pattern matching query is also a grounded symbol, and we can actually have some knowledge in one space. We can import it as a new grounded symbol, and we can perform pattern matching over this over this atom space, and we will see that we don't have any code about color of planets, but if we put self here, it will not work. So the result will be empty. If we put self here, we can import stuff from other files to this atom space as well. And again, it will have result derived from the content of another atom space. And hopefully, when we attach a distributed atom space backend, we will be able, if we want, to perform some large-scale pattern matching over huge metagraphs. Then we will just import this distributed atom space as a certain grounded symbol, and will do pattern matching of it and retrieve results to the interpreter to do next queries, chaining them with automatic chaining with the use of equality queries and so on. Okay, well, I guess we don't have too much time, so let me talk a little bit about the
Alexey,
latest.
we have plenty of time. Just so you know, we're not taking lunch for another 35 minutes, and I'm gonna post the questions.
But there is also Vitaly who will be present in his part in our mutual talk with him, and then we will have Neil and Hedra with another talk which also will take 1 hour at least.
Right,
So yes,
in the afternoon after lunch, right?
Okay. In any case, the most novel part, which Vitaly and me were working recently, was fleshing out behavior of MeTTa in presence of type definitions. Actually, we consider it 2 ways, and I will not say that we have already ruled out one of them. One of the ways was to introduce type operations in MeTTa itself. So we can use pattern matching, which is a really powerful idea, and we are very thankful to OpenCog Classic that we brought this borrowed this idea from there. So it's really a way to make meta languages. So you can use pattern matching to create your own type inference or whatever, but it has some difficulties. Right now, we are working with type checking and type inference implemented in the core implementation language, namely in Rust. But we still hope to parameterize the interpreter in such a way that you could easily change the interpreter behavior with respect to the type system, but it has not yet been done. There are actually many complex plans, and what I am talking about is a very, very basic core component of Hyperon. It's not even MeTTa language in general, but just a very core component of this MeTTa language, and there is a long way, but hopefully very fun and interesting way ahead in development of MeTTa, because we are now approaching to even more fun stuff than we already have here. Okay, so actually one place from which we encounter the necessity to work with types is basically grounded symbols, because if you write plus S Z without having anything about S and Z, it will not just be reduced because we don't have equalities for this type of expressions, for this symbolic expressions. In normal functional programming language, it will not just compile, but MeTTa is much more loose in terms of what it accepts. I would, well, I'm absolutely not an expert in the Wolfram language, but the only thing I remember from it is that it works with symbols in a similar way. So if there is some symbol for which we don't have rules what to deal with, we just keep it as is. So if we have some rule, then yes, oops, it will be reduced. So it doesn't care what S actually is, and in the piano arithmetics, it's actually will be an incorrectly typed expression, but we don't have types here. It will just see if it can reduce this expression or not. But if we have grounded symbols, then how should it deal with something like that? And in this case, it will actually return a sort of error which is not shown because it's an intended behavior. If we have incorrectly typed expressions with no turned on automatic type checking, then these expressions are reduced to void, to empty set, to absurd. It's not an absurd function. Never mind. Okay, so actually, grounded symbols are not very hiddenly typed. Will it work? Yeah, it works. So it's basically a number. It's a Python wrapper, and it doesn't distinguish between different types of numbers. It's also, well, it's not part of official library or something like that, but just current state. Maybe it will be changed. In any case, this is a number. This is a string. I don't know what will happen if I type something like this. Yeah, it's a space. If we ask what is the type of match, it is some function from space, atom, undefined. I will not go into detail. Let's just take a plus. Yes, and it's a function from two arguments of type number, and it returns number. So actually, it in the course of reduction and application, the interpreter checks current types of symbols, including grounded symbols. Most non-grounded symbols are undefined. So we have a sort of gradual typing here. But we can, if we want, and we typically do want, we introduce types. Say we want let's introduce a there. Type, which is actually a parameterized type, and it has two constructors, and we can say left 5. It will be not reduced to anything, but if we try to get its type, it will be as a number, which makes sense. So we can have a sort of sum type. We can have a sort of product type, like a pair. Again, it will not be reduced to anything because we don't have any equality here. But if we try getting its type, it will be a pair of string and number. It also makes perfect sense. We can also have recursive types, like lists. And the type of this list is basically list number. And the type of this list is empty because it's not a well-typed expression. When we, I don't know what will happen. Well, and since it's not well-typed, it will be reduced to an empty result. If we didn't have type definitions here, then it will be just the same. It doesn't output a string as a string. Maybe it is a little bit confusion, but in any case, so what I would really like to emphasize, one of the ideas behind MeTTa in particular was that basically type checking in algebraic and dependent types is the same form of pattern matching, but it's just syntactically different in languages like Haskell or Idris, but it's actually the same pattern matching, and this is why we were thinking about the possibility to implement typing as in MeTTa itself. So you just have some typing rules, and these typing rules can perfectly be expressed as pattern matching queries. Maybe it's better to call this unification, I'm not sure, but whatever. However, there are some obstacles. Again, it's a long story, but right now we don't use this form of implementation because there are many complications dealing with grounded symbols, and actually we have meta types in MeTTa itself. Maybe I will talk about them a little bit later. But what I wanted to say is that these are also just symbolic expressions with variables and you can make queries over them if you wish, but it's maybe its behavior will not be always as expected. But if we have something like red is color as a type, as a type in expression, then you may try to have match self X color. Which colors do we have here? And yeah, we will get red. So it's just an nearly ordinary expression. It also has some additional semantics inside the interpreter, but in our space, it resides as an expression. By the way, we can inspect the content of the current atom space, we can add, I don't remember precisely. Will it work? Yeah, and we will have this SS expression in the atom space itself. But we will not have these expressions because they're executed right away. But you can have some function which inserts some atoms to the current atom space or any other atom space. So as I mentioned, match doesn't automatically put its result to the atom space, but you can actually do this in addition if it's necessary. Okay, going back to the functional programming stuff, we can implement higher order functions in MeTTa. So, for example, current function will have a type something like that. And we can have a funny implementation of carry without having lambda, which is also not possible in normal functional programming languages, as far as I guess, because we can have any pattern here. It's not necessarily an application of a function, but it's an arbitrary expression. And in this case, we can get type of current. Wait. Sorry. Okay. So current version of plus will be a function which returns a function. And well, it's if we apply carry plus, then it will not be just reduced because there is no equality for this kind of pattern. But if we apply carry to something and something, then it will be reduced. So because it will pattern match against this expression. So and there is no mystery what is going on because it's quite transparent in terms of pattern matching. While I remember when I first encountered partial application of function, I was wondering what is happening there. So there is a partial application, but you can there is no code to transform. So what is happening? What is happening? There is just no reduction. So we can we are keeping this non-reduced expression, and once we apply it to enough arguments, it will be reduced. So in MeTTa, it's for me personally, it's more transparent, at least if we are implementing this in a certain way. Okay. There is one more interesting case of higher order functions. It's fmap. And once again, and funny thing about MeTTa is that we can implement a very general form of fmap, which is applicable to different functors. If the constructors have the necessary pattern style. So, for example, we can have something like this, and we will not need to derive implementations of fmap for. Okay, let me reduce carry here. It will be helpful. This form of carrying. Okay, and if we apply some function to a container constructed by some functor, then it will just work. So we have a very generic definition of fmap, which knows nothing about the functor maybe, and if we put nothing here, with some exception, we need to have it in this way. So it will also work quite well. We can have left 5, it will give us left 7, and so on. There are some limitations to this, but it's quite funny that on this generic pattern matching, we can have a generic fmap which is applicable to different functors without special procedures for deriving implementation of fmap to them. So it works purely on pattern matching, which is I find quite interesting. And okay, the last thing which I would like to discuss now is dependent types. So it was Ben who I would say insisted on considering dependent types in the design of MeTTa, and it indeed very interesting, and Neil are using dependently typed languages in AI DSLs right now, and yes, it's very interesting stuff. And we have a sort of dependent types in MeTTa. Again, on this, well, since it is implemented in the core, I wouldn't say that it's purely on pattern matching, but it could be on pure pattern matching in some way or another. So we can implement a classical example of dependent types. It's a list with a known size, and its size is encoded in the type itself. For example, if we get a type of cons 0, cons 1, nil, we will get this result. So it's a vector of numbers of length 2. And we can have something in addition. Say we have a function drop. And if we consider the type of this list, it will, without executing drop itself, it will give us that the result will be the vector of numbers with length 0. An interesting thing, what will happen if we try to do something like this, and the result will be empty. So actually, it perfectly corresponds to the fact that this expression is badly typed. It doesn't have a good type, and it's interesting how it works, because drop function has this pattern in its definition, and it simply doesn't, it cannot match with nil here. So it doesn't pattern match, and thus it doesn't retrieve the correct type, any correct type for this expression. There is a long discussion on how to represent knowledge with the use of types, and some time ago Ben how to say advertised the book on model homotopy type theory for natural language understanding, philosophy, and so on. But personally, I find some inconvenience with representing everything using types. But I guess it's a too advanced topic, and we don't have too much time. I would rather say another thing. MeTTa actually doesn't implement fully fledged dependent types because it doesn't have totality checks. It doesn't insist on the totality of functions, so we don't need to have all cases for the function over some type. We actually don't distinguish between functions and constructors. So if you just remove some equality, it will just not reduce. So it will work as a constructor. If we return this definition, it will work as a functor or as a function. Yeah, so if we execute this, it will return nil. So it works like a function. And because actually functions can be partially defined, and in some cases they will work like constructors. In some cases they will work like functors. So for example, in this case it will not work, I guess, because of the type definition. But if we put it this way, drop nil, then it will just not reduce. It will remain the same. In this case, it will be reduced to nil. So it's questionable and discussable whether this approach is good or not, but I find it quite natural from human reasoning perspective, because for example, you can know how to calculate an integral from some one function, but not from the other function. And in one case, you will reduce it to some expression. In another case, you can deal with it as is, hoping that it will just go away in a certain place, or just keep it until the end. But what we are losing here is basically mathematical induction, because what is very powerful about dependent types is that you can prove general theorems. So I'm not sure. Okay. So for example, if we are trying to represent knowledge in type system, we can have some entity type, and this is also discussed whether dependent types are good or not, because we either should have some very, very generic type, and everything else will be predicates and so on. For example, we have this: humans are mortal. So it works perfectly well when we want to infer something. Say we know that Socrates is sorry? No. Okay, yes. Socrates is human, and in this case we can get type humans are mortal, Socrates is human, and what we get mortal Socrates. So basically this is an instance of this type, and in accordance with the idea of types as propositions, this is actually a proof that Socrates is mortal. And the question is, what is this? It can be either an assertion or it can be a theorem to be proven. But in our case, we cannot represent this as a theorem because we don't check totality, and if we could mark it not as a constructor, but say something like this, and in this case we could enumerate all cases like humans are mortal, Socrates is human, and Socrates is mortal, which is not presented actually here, so it that doesn't work. So and the same for Plato. Then we could say that we proved that humans are mortal. I don't like this idea for real world knowledge because it's not a theorem. We can list all the humans and say they are mortals, but well, it doesn't work like this. But on the other hand, it works in mathematics, and at the current stage, we are kind of losing this. But we will extend the MeTTa language with some additional type annotations, like I put it here. It could be like this, or I don't know, another symbol here, or something else. So we will say that these symbols are really should be treated like total functions, and in this case, if we can provide an implementation for this function, then this implementation proves the statement encoded in the type of this function. But once again, it's maybe a long story ahead. In any case, I wanted to make it clear that there is a difference. There are strong sides with how MeTTa is loose in terms of dealing with non-total, non-deterministic functions and so on. But it also has a downside. But hopefully these downsides can be dealt with. Okay, I hope it's enough from my side. Maybe Vitaly can have like 20 or 30 minutes to peek under the hood of the implementation. Is it okay?
Okay, that sounds great.
Okay.
Thank you very much. And now we will have Vitaly Bogdanov. Here you go.
Yeah, thank you, Alexey, for presenting us some kinds of meta expressions. Yes. Yeah, I'm starting my video. And I will share my screen now. Okay, right, it should be visible. Yeah, I'm going to be more technical here and give you some introduction to the Hyperon experimental repository details, how the Hyperon library is looks like under the hood. And yeah, I will be trying as short as possible here because API is quite large, but I will cover only.
You have 24 minutes. So
yeah, okay.
Okay, all right.
Okay, I will try use them all. Okay, first I would like to start from the from describing what repository has. Repository has three main components in here in the. So the main one is a Rust library Hyperon, which effectively implements all the functionality Alexey just shown, almost all of the functionality, and it is a core library written in Rust. And we also have some C API library, which exports Rust API as a C API. Its intention is to serve as like universal API for other platforms. And one example of usage is a third part of the repo is a Python library, which Alexey used to show user examples. So Python library has probably the mostly developed MeTTa, some kind of common MeTTa symbols library here. And Errol shows the dependencies. Okay, we use CMake to build it overall, but Rust library can be built independently using Rust tools. Okay, the next thing I would like to show you is what is the inside of the Rust library, which API it exposes. I will use auto-generated documentation, which cannot be found at the moment in the common Rust places like crates.io site, but we are going to publish the library in nearest time. Before this, one can generate this documentation using the instruction and README file of the repository. Okay, so Rust library basically has four main parts, four main crates in Rust terms. The core one is an atom crate, which contains main types and functions to create and introspect atoms. The second one is a space crate, which is basically a place to put Atomspace integration code. Actually, it is a place where some integration with big atom spaces will be developed, but at the moment it contains the only version of the in-memory atom space. Third part is a MeTTa crate, which contains all MeTTa-specific functionality like interpreter, some different predefined MeTTa atoms, atoms which are specific to MeTTa, like equality symbol Alexey just demonstrated. Yeah, and some type check and text parsing stuff. Okay, I will try to core the main atom crate. So the core of the crate is an atom type, which is simply the sum of the symbol, expression, variable, and grounded atom types. So we have 4 different kind of atoms, 4 different kind of enums here, and they're pretty simple. Atom also contains 5 constructors. To construct the symbols to totally hide details of the implementation to make it possible in the future to change the implementation under the hood. Okay, symbol atom is pretty simple. I will show code here. So it's just a structure which contains a name and has a couple of methods, exactly constructor and method that returns the name, that's all. According to the Rust common rules, it implements, I will show it here, a lot of standard Rust traits to be possible implement them for the atom itself. Okay. Okay. The second kind is a variable atom, which is very similar to the symbol one because it also has a name, but also has some special field. It's a technical detail, but very important. You can create, using this field, you can create some unique instance of the variable. Or if you have an expression and you will like to make the exactly same expression, but with unique variables, you can do it using this field. It is not needed like to fill it manually. Variable atom has special method make unique, and atom has atom create has a function to create the copy of the atom with unique variables inside. It's massively used in the matching and in the querying of the atom spaces because each query returns you data. If it returns new variables, they are MeTTa guarantees that they are unique. Okay, third kind of atom I would like to explain is expression atom. It's also very simple. Basically, it's a collection of other atoms. And it's as simple as that, just vector of atoms. And it may contain different atoms, including other expressions. And it have functions to get children and even to mute children. So it's a mutable atom. You can work with it in place. I mean, you can edit it without creating new instance. It is not a requirement of the implementation, but it's like detail need to keep in mind when working with expressions. Okay. And last and most complex kind of atom is a grounded atom. It has 2 different constructors to construct instances. It is because in Rust, okay, it's not maybe very Rust specific, but actually first constructor atom value allows the user to wrap into the atom any common Rust value. You don't need to code something to wrap it into the atom. You just need to call the constructor and pass the value into it. But the value should implement some specific trait. Basically, it means it should be it should implement equality trait, should implement clone, debug. Sync is usually implemented automatically. So, and it should be static. It's also a requirement. So you need to be able to construct this value at the compile time, not dynamically when program runs. If these traits are implemented, you can just wrap this value into the atom. By the way, as it is an example how to create atom in a pure Rust code. So you can just call the constructor, passing it to the value, and you can check what happens. Convert the atom into a string, for example. Okay, the second constructor is more sophisticated. It requires actually one additional trait, but it allows user wrapping some custom types with custom behavior. It's very interesting, and it is what is actually exploited when someone would like to define new grounded atom with some specific behavior, and user can modify 3 aspects of behavior. The type of the atom can be modified. So if one implements the grounded trait, it can implement the function type, which returns any type it wants, he or she wants to this atom to have. There is also execute function, which allows you wrap not just data, but also some behavior into the atom or a function. Or this function is executed when interpreter would like to call the atom which is represents the function. For example, probably. Okay, yes, I have some example here, but it's just trivial. Like you can write some function here, and if you are executing expression which contains okay, maybe it's better to. Okay, I will try to put it in words. So if you have an expression, the first atom of the expression is a grounded atom, and other atoms are considered as arguments of the grounded atom. So when interpreter tries to execute this expression, it checks whether the first atom is grounded function, and if it is, it calls the execute function of the atom and passes other atoms as arguments to this function. The function can return non-deterministic result, like many different atoms as result, or some execution error. And third aspect of the behavior of the atom you can modify is a matching. It's a function one can implement to customize the matching of the atom. Usually atoms are matched by, like grounded atoms are matched by equality. So two grounded atoms match to each other if they're equal. But one can implement some dictionary grounded atom, for example, which have more complex behavior. Like if it's matched against some pattern with variables, it will return like few atoms from inside from the dictionary in response, and it allows modifying matching behavior in the grounded function. For example, there was some like before there was a topic raised when how to like match non-symbolic neural network data with symbolic expression. For example, like one of possible ways is to implement custom match function, which will do this match between those kind of data, this kind of data. Okay. Hyperon atom. That's all about basic atom kinds. The next topic is matching, or it's massively used in the MeTTa language, and actually all things Alexey showed exploit this function, match atoms. This function gets two arguments, data and pattern. These arguments both atoms, but they are not treated equally. So data is a kind of restriction to the pattern, and provides some data to pattern, and may apply some restriction on pattern paths. Pattern may contain, both of them may contain variables, but only pattern variables are returned as a result. So the result of the function is an iterator over binding of the variables. Okay, I will show that it's like some complex Rust boxed iterator with bindings, and bindings actually is just map of variable atom. This like variable without atom wrapper to atoms. So when match atoms, by the way, I can make it larger. When match atoms returns bindings contains only pattern variables as keys. For example, how does it work? If we have two expressions, okay, I will explain it what experiment mean later, but now you can just okay. Yeah, imagine that it is an expression, and this is a symbol, and this a is a variable, and here we have an expression with three variables, x, x, and y. How does it work? So according this pattern and this data, variable x will receive the value of the symbol v, because x and y are equal according to this part of the data. Y also will receive the symbol v as a value. That's basically how pattern matching work. There is interesting special case of this matching where you have expression with two variables. For example, we have such data with two x's, and we have a pattern with two different variables. Effectively, matching these two atoms means that A is equal to B, but matching algorithm will put it in in its way. It will create additional variable and will put both A and B binding will bind both A and B to this variable and will return this result. After matching is found, you can use different functions like apply bindings to atom, apply bindings to bindings, and if you will apply such result to expression which have both A and B, it will effectively has one variable which will replace A and B, both A and B. So this is how pattern matching and MeTTa works. Okay. Okay, I will not explain sub-experiment crate. It's really simple and almost not used now. It contains some algorithms to walk through the sub-expression in different ways. Okay, next interesting crate is a space crate. Yeah. As I said, the space crate is like a place to keep different implementations of the space and Atomspace. And now We have the only implementation. It is a memory space which contain grounded atoms, which can contain grounded atoms, any kind of atoms actually. And it is actually very simple. It's also just vector of atoms and have different methods to add, remove, replace atoms and make queries. Now it's like simplified API, but what we are going to do next, for example, to integrate with Andres Sena implementation of the Atomspace, we are going to introduce a new trait space and implement it independently for different cases. Like this one implementation will be in memory Atomspace, and it can be another implementation like Andres Sena implementation, which is distributed large Atomspace, which contains tons of data and may match them effectively, or just another one like disk database or something like this. Okay, that's all interesting about space. And MeTTa. MeTTa, the most interesting part of MeTTa crate is the interpreter crate. I have the long description of the interpreter algorithm here, but I will not read it now because of time. But interesting is that interpreter, actually we have one function interpret which takes two arguments, space and some expression, or actually atom, but usually it is expression, and interprets this atom according to MeTTa rules, which Alexey explained, and returns some result. It may be some like list of vectors or some error with some human readable explanation. But interesting thing here that interpret itself is implemented through two other functions. It's like a loop. Sorry, I will make it larger. It's a loop which continuously calls interpret step function. And these two functions, interpret init and interpret step, also exposed as public API and can be used to make self-aware interpreting of the MeTTa expression. So if you have some like, let's say, MeTTa algorithm, which need to interpret some expression, but consciously, it should not just run this function and it, for example, may expect that function will never end. It can run interpret step in a loop, and after each step, examine the result of the step. At the moment, it is not like it's not quite possible to do this in MeTTa itself, because interpret step is interpret set returns some Rust specific structure, which cannot be just like out of the box analyzed by MeTTa programs. But there are two different options we have, at least for now, at least two different options we have how to do it in future. So the first one is to implement the space trait for the step result, for example, and then the result of the interpreter step will be effectively an atom space, which can be queried, which can be analyzed by MeTTa program itself. It's the first one, or first option. The second option is to return the result of the step as an atom, and it also will be like possible to analyze this atom by the MeTTa. What actually step result contains now, it is a plan of the execution of the function. So if of the expression, sorry. So if you have an expression, each interpret step makes some small step in interpreting it, and forms the new plan for the future, and returns this plan into the to the caller. So this plan basically has three different options. It can return the value, and then interpretation process stops with returning the value. It can be an error, and then interpreter just skips this branch of interpretation because it knows that it doesn't make sense from the point of the interpreter. And it can be another plan. Okay, this is how interpreter works. Okay, yes, I actually. Okay, because calling atom constructors like oh, sorry. Atom this one maybe too verbose. Actually, there is a macros in the Rust code, which can be used to somehow simplify instantiation of the complex expression from the Rust itself. It actually interprets any string as a symbol, any identifier as a variable, and anything in brace it interprets as grounded value. Okay. That's all about Rust API. Oh, I have probably 5 minutes, so I will just briefly show you what other parts of library has. The library actually is quite simple. It also has Rust code, which exports Rust, which contains Rust functions with some specific marks, which allows Rust SDK to generate C API for this code. So like it is a Rust function which will be compiled into the function with C calling conventions and can be called from the C code. So basically, it is just manually written converter from the C API to the Rust API and back. It's quite simple and straightforward. And finally, Python library also has a part which uses C API using PI bind library, which is commonly used to generate Python API for C code. So it's also very straightforward, just a list of calls, which are usually just calling C code and returning the result. All wrapping of Python values and like from Python values to C values and back are made by the PY bind library. And final part is a pure Python library, which uses Hyperon PI native library as an backend API. It's organized a bit different, like comparing to the Rust API, because Python doesn't have such rich algebraic data types abilities, and it's organized as a list of classes. Each kind of atom has its own class. We have symbol atom, variable atom, expression atom. Each of atom has specific methods which calls C functions, actually. So the Python library is just a thin layer of the Python API which calls the Rust core library. Okay, what's interesting there that it extends Rust API in some way. For example, Alexey wrote here some special functions to create to quickly create grounded atoms from Pythonic lambdas and functions, and like it is kind of two-way street. Like Rust API contributes to the Pythonic one, and when Python API has cool feature which can be ported into Rust, we are also moving the Python code into the Rust core. So if one would like to experiment with Hyperon and don't know Rust, for example, he or she can use Python to experiment. And if there is some interesting API which can be moved to core, we can move it easily. We do it with Alexey, did it many times. Interpreter is also looks like class, and there are some type-related functions. Okay, that's all about REPA, which we have, and yeah. Usually unit tests in each directory here contains interesting examples in the Python. For example, Python test probably the mostly developed bunch of examples has scripts in pure MeTTa language, which is interpreted by Alexey's MeTTa interpreter implementation. So API is continuously evolving, but now you can already do interesting things with it. And yeah, if you want to contribute, you can just fork repo and make a pull request. Okay, thank you very much for your attention. I hopefully did not take more time than I had. Okay, any questions on this? Or maybe, yeah, me and Alexey can answer question if we have time for it.
Right. Unfortunately, we don't have enough time for questions because we're going to cut to lunch. But we will be back at 2 p.m. Neil Gayswiller is going to take over at that time, and then we're going to have a Q&A session where people can ask questions of all of you. Right, so thank you very much.
Okay, thank you.
Because the time's crazy where you are, huh? Didn't think about that. Okay, so I'm sorry, we've got so much packed in today. Okay, so now we are going to take a break, and I will be back at 2 p.m. And everybody, we will see you then at that time. See you at 2 p.m.
Thank you so much, Alexey and Vitaly. Fantastic talk. So we're going to take an hour now for lunch. We can take questions for Alexey and Vitaly on a separate YouTube stream as a follow-up to the conference. So stay tuned and we'll email you for all of those, and keep those questions or write them down and send them to me. Now I need to tell you all where to go for lunch, but I don't know where to tell you. Does anyone know where we're going for lunch?
There was an email.
There was an email. What did the email say?
There's two Rocco's Pizza, Belltown Pizza, some random bar is the name. Vanguard Market, Donair Box, Iron One, Alpha Shop. Well, I feel like pizza we do but I'm down for other developers. And the grass fed burger place for a half mile away. In general, seafood is good. Yeah, in general, it's see that. Yeah, I mean, I live on land. It's like a couple of COVID, it's like really good. Yeah.
Right,
Walking out the door.
walk to Second, Sarah's saying walk to Second Avenue and turn right, but I don't know where Second Avenue is. For a bunch of restaurants.
Second Avenue, one block out.
Is that fight?
Yeah. All right.
They have a very colorful stories. New step forward in the AGI, it's like
Yeah, it's maybe the more, it's thinking about it, I'll read it out.
Yeah. It's. Yeah. Yeah, I don't have so much thing. Ben's internet does. It's really bad, so many encouragements.
We get it to the 3 month.
Did you make that lunch time?
I don't think.
Donner Cabal. Yeah, Ben. Oh, I went. I don't know if you've seen this, is one of the sort of mid-period papers.
What,
Mid-period, I mean, I think. Like, well, after the stuff he was talking about in his lecture. And then it's a little more, it's a little before. Where where did you see them go? Down. I think that, right, we didn't see, I didn't see, we lost. You didn't call him. But yeah, his talk and then Conrad's talk. For Alexey. And then this, I started going into this, and it started to gel in my head.
Yeah.
Yeah.
You heading up to lunch?
I'm gonna take advantage of it.
So I already know this stuff at the level of you get into this presentation. I can get it, deep level actually.
Yeah. looking for it too. Right? Tony was just looking for it. Yeah, they're going to do this.
Are we ready to start?
Hi, Neil.
Hi, Matt.
Hi, everyone.
I'm the only one here. In the room, that is. I'm going to give it a few minutes.
So how much time do you think we should allocate to our presentation, Matt?
So how much time would you think it takes?
So like
We
I
have,
the range I would give is like minimum would be half an hour, maximum would be, well, I mean the maximum is always difficult to evaluate because depending on the tensions that come on the way and the questions, and it can take a while, but
yeah, just looking at the schedule, we have 3 hours and 4 presentations.
right. So yeah, that's
So that won't give us a chance to do the last part, which is pending topic or open discussion. So
Right.
maybe if we do, let's see, it's 2 o'clock here. We have until 5-ish. Sarah?
Yes.
Sounds good. So if we each do each of the 4 presentations a half hour.
okay. We're gonna aim at that.
We're going to aim at that. And I do see people online. But there's still, no, it looks like there's people are arriving now. So let's just give a couple minutes and maybe start in 5 minutes.
Okay.
Does that sound good, Neil?
Oh yeah.
Neil, do you have time limitations in the venue? Like you should finish at 5 p.m. no matter what?
Yeah, we're gonna be starting soon. I don't have any control over it. It'll be just a minute or two. So, and we're live right now, so it'd be better to use chat. Okay,
Lisa, can you hear this okay? Lisa, can you hear?
Yes, we can hear you.
Thank you very much. Is the audio clear for a presenter that's over here as well?
It could be better.
Can you hear me?
Yeah, I can hear that. That voice sounds like it's got a microphone.
We can't hear your audio right now. The volume's all the way down. Can you say something in chat?
My volume. Who are you speaking to? Can you hear me? Can you hear me, Haley?
I could hear that, but I don't know if they hear you.
Everybody's hearing us on the YouTube channel right now. So
Right.
For the output to the up here. The sound output. Matt, where was it Zoom from? Speaker. Oh, I put the speaker as the microphone. Sorry, we want this. And then while you're
That's the.
okay, I muted you again.
By the way, how is my audio? Is it
Your
is it
audio
at that
sound.
level?
Yeah, your audio sounds great.
Okay, cool.
Yeah, and we're just really super like 1 or 2 minutes away. I'm so sorry for the delay.
Oh, no problem.
Okay, thank you.
Hi, folks. Can you hear us?
Is it off mute?
Can you hear us from
Yes,
London?
we can hear you. Do you want me to turn your camera back on?
Is it better now? Is this audio better than before?
Much better than before, but still could be louder.
And you might be able to turn it up here too. Joe, we might be able to turn it up here too if they need to. I'm not sure.
Okay, let me know and I should cut to your video.
I don't know where the London next. Okay, we're ready to go. Are we ready to go? Are we live? Or you can sit behind the bar if you want.
You want this right here? Yeah.
That's all right.
I think so. I'm just waiting for them to tell me. All right, everybody, welcome
we're
back.
good.
Thank you for joining us. Thank you. Sorry. Thank you for joining us here in Seattle for AGI-22. We're back for the afternoon of our OpenCog scaling up OpenCog Hyperon discussion today. And our next speaker is our very wonderful Neil Geisweiler. And he's going to be talking to us. Dr. Neil Geisweiler and Hedra Said Yusuf are going to talk us through towards porting procedural and temporal PLN logic to MeTTa. Thank you very much. Big welcome to Neil and Hedra.
Hello, everyone. Actually, I can't start my webcam. Not that it's crucial, but start.
Sorry about that. You should be able.
Right.
You should be
Okay.
on right now.
All right. Yeah. So I guess let me share my screen. So I have a small presentation, and then Hedra and I we will make a demo of the work that we have done. So okay, let's get to it. So I think you are seeing some slides, correct?
We sure are.
All right. So yeah, so basically, I mean, we've had for a long time a version of PLN for OpenCog Classic, and now that we're moving to a nicer system, we're trying to port this work. So the work that I'm going to show it's mostly some core parts of PLN. We're not yet at this point at the temporal and procedural reasoning aspects, but I'm going to touch upon that a little bit as well. Okay, so I'll jump right into it. So I'm going to recall what is PLN. So what I'm going to recall is just a small set, just to be clear. So we're going to start with defining collection of predicates. So what are predicates? They are just a tuple of atoms, and they return true or false for a given tuple. Okay, there are subtleties. It could be fuzzy and probabilistic, but we're not gonna expand on that for this presentation. So you may safely assume that there are just traditional predicates returning true or false. So right here already, there is a little bit of correspondence between what we used to have in atomies and what we now have in MeTTa. So I'm going to go through that, and there will also be some sort of recall. So the first thing we have is we can have a predicate, and we can associate a true value to this predicate. So in math, it's something that we could see as kind of meaning the probability of the satisfying set of that predicate is an approximation of the mean of the truth value of this predicate. Okay, I haven't told exactly what is the truth value, but I'm going to tell you right away that it's like a probability, but it's a second order probability. So it's a distribution of probabilities. And so that's why I use the symbol approximate, because while in the case where the truth value is actually a second order probability, well, it's more than just a mean, a number. It's an entire distribution, but it still captures this idea. Okay, we have then the traditional connectors, logical connectors. Not is basically we take the probability of the complement of P. We can take the disjunction, which corresponds to the union of their satisfying sets. Same idea for the intersection as the disjunction. That's there. All that is pretty natural. We have the implication that essentially means that the probability of Q knowing P, well, is approximated by the truth value over the implication. And we have also individual observations, one might say. That is, we take a predicate and we take a particular tuple and we evaluate this particular tuple over the predicate. And we can tell, again, what's the probability of the predicate being true for this particular tuple. Okay, so now let's go to MeTTa. So, okay, you can see that we have basically, we are expressing, I mean, it's a rather flattened way of describing what's going on. We've got the predicate here. This M, this equal sign with an M above it, it's called measured by. And what it says is that the predicate P is measured by its associated truth value and so on. And we just use measured by everywhere. And if you wonder, well, okay, is it really a MeTTa code? And the answer is yes. MeTTa supports Unicode. And so, well, I mean, why not use Unicode? At least we're playing with it. We'll see if it's really a good idea, but it is this way for now. All right, so now, okay, we're once we have these, so okay, just again to remind you, this is just a small subset. There's a bunch of other stuff, but I'm just restricting the recall to that subset. Again, I'm restricting the recall to a small subset of rules. I'm just going to present two of them. We have the deduction, which is basically the transitivity of implication, but probabilitized. Okay, P implies Q and Q implies R. We can infer that P implies R with a certain truth value, which is calculated according to this formula. Okay, I'm going quickly over that, especially because we are under tight schedule. We have the implication direct introduction, which creates an implication from samples, from observations, you might say. So, for instance, okay, we have observed that when P is applied to A1, well, we observe this truth, whatever it might be. When Q is observed over A1, we observe another truth value, etc., etc. And with this, we put all that together, all these observations, and we can calculate an estimate of the truth value of the P implies Q. And all the formula is fairly straightforward. I'm going rapidly anyway, but that's what we all know. And however, there is something a little bit subtle about this inference rule, is that there's an arbitrary number of premises, and that can be problematic. It's like, depending on the premises that you choose, you're going to get a different truth value, etc. So actually, well, something that that I want to say is that as we are porting PLN to MeTTa, this is our opportunity to basically make things right. And so I'm going to show you just in the next slide how here we can make things right, because in the OpenCog Classic implementation of that rule, well, the rule actually takes an arbitrary number of premises, which can be problematic, leads to pathologies and so on. So in MeTTa, we're going to do something different, but I just need to walk you through a little bit what are truth values. And so I have to be very careful about the timing. So I've been talking for 10 minutes, I think. Okay. So basically, we have the traditional truth values, but here they can be explicitly Booleans, or basically a single number or probability, or they can be a probability and a number of observation, probability and count. And we have methods associated to this type. So this is real MeTTa code, as you probably have recognized, and we introduce a new type of truth value, which is the evidential truth value, which is going to hold not just a probability and a count, but also an evidence set. So in OpenCog Classic, we had almost that. We had an evidence count truth value that holds the number of counts of evidence, but here we hold the evidence themselves. And this allows us to not fall in that sort of pathologies that we had before. So, okay, it's just to give a little notation, this is going to be the truth value. If you are used to PLN, well, as it was described in earlier books, this is going to be familiar. And for the evidential truth value, we have a pair, which is first an evidence set and second a truth value. And so once we have that, we can reformulate this implication direct introduction rule in a recursive manner. And so, well, I don't have a lot of time, so I'm not going to go over that for too long. But you know, things they make sense. I mean, if you look at them, it makes sense. If you have no evidence, well, the count is going to be 0, and then you can accumulate evidence, and you can make sure that you don't double count evidence. Okay, with this premise. And here's an example of, for instance, inferring P implies Q given evidence A and B. All right, and so what Hedra and I were going to show you are these two rules implemented at various levels of completion. We tried many different approaches Some are, well, more or less complete. There might turn out to be good ideas or bad ideas. We at this point, we are really just in exploration mode. So just to touch a little bit on the temporal and procedural reasoning, I just want to say that once we have these working well, implication, direct introduction, and deduction, basically doing temporal and procedural reasoning is almost given, because basically we can reframe, for instance, temporal deduction into regular deduction. So this is the inference tree that describes this reframing. Same thing for temporal procedural deduction. So the difference is just that we have actions as well. So same thing, we can reframe that as regular deduction. So that's not exactly where the difficulties are, not at this conceptual level anyway. Okay, so I'm done with my presentation. I'm gonna walk you through quickly the implication direct introduction rule, the various versions that I came up with, and Hedra then will walk you through the deduction, the deduction rules, and how so far she actually has been able to combine the tools together. So, all right. So let me see. Okay, I guess I'm gonna start with. So there's a lot. I mean, there would be a lot of stuff to show, but I'm gonna have to be somewhat selective. So, okay, I'll start with this one. So basically, all that you see here are well, all the various implementations of the implication direct introduction. I'm going to start with the match version. And why I'm going to start with that? Because this is really the closest thing we have to OpenCog Classic. Because match can be seen as being a bind link, meaning a call to the OpenCog Classic pattern matcher. And so, well, it's fairly straightforward. We have the premises are in the patterns to match. Okay. Hold on. I should begin the beginning. So, oh well, no, this thing is wrong. Okay, so I'm gonna, well, yeah, keep presenting that thing. Well, so basically, okay, we have the premises. So this is for the inductive version of that rule. And here we have the conclusion. I mean, if I bring back the rule, I mean, this is just coding this one, really, just very literally. Okay, and so, well, we'll see how we can use that to do some form of chaining. It's not the best way to do chaining for the reasons that Alexey described this morning. But it is actually possible. So another way would be what I call the entail version. So basically, the idea is to ignore for a moment the fact that we can use matching and equality, and just think of these proofs as just relationships. And so we define a relationship. So that would be something that would define the the axiom of the implication direct introduction rule, and that would be the relationship that describes the inductive version of that rule. And okay, what are we going to do with that? We don't know yet. Probably we'll need to define some equality to have things work together, etc. But that's the idea. Okay, there is the I would probably say the idiomatic way to do reasoning with MeTTa, which would be using equality. And so, so here, for instance, that would be the axiom. Since it's an axiom, we don't need actually to define any equality, but we do need equality in the case where we have premises. So, what is that? Where do I get that? Oh, it's backward, forward. Well, so there's something interesting with the equality because we can actually define something that goes forward and backward using equality. So this is what is expressing here. And okay, what are we going to do with that exactly? It's still unclear. We haven't used exactly chaining with that. There are some problems, such as here, for instance, we don't have constructors as far as computing the formula of the truth value. So there might be some tricky parts here because, like, reversing, basically going backward on the formula that calculates the truth value itself could be a bit tricky, but okay, as I say, we're just exploring. And so there's one last interesting version, which is using dependent types. And so in that case, the proofs are programs and the propositions are types. So that would be one example where we can associate a constructor to that proposition that corresponds to the axiom of the implication direct introduction rule. And here we also associate a constructor to the inductive version, but because it's inductive, it has premises, and the premises are present in the arguments of the constructor. And so so that's what we have. And I think from there, you can take it from there, Hedra. I'm going to stop sharing my screen.
Oh, okay, sure. Thank you so much, Neil. Thank you, everyone. I will be sharing my screen. I hope you can hear me.
Yep, can hear you very well, Hedra.
Can hear you great.
Okay. I will be going through the reduction rules, the MeTTa port. So I will not be presenting the rules here. Just I will go through the implementation. Like Neil mentioned, we do have a few types of implementations, and the one you're seeing is of the Intel version. So with the Intel version, I like MeTTa has given us, the option to actually define our own symbols as a way we like. So like Neil mentioned, this is the Intel sign or the Intel symbol, which we will be looking for the premises here in order to do the deduction. So we might not be, each incidence might not be considered here. We will just look for the predicate. If there is P, Q, R, and P actually implies Q, and we know that Q also implies R, then we will see that P implies R, and we will actually derive the formula or use the truth value formula here and find the truth value for the P implies R. So for that, we do have a deduction formula here, which uses a couple more helper functions here, as you see. Like it's actually the exact same copy of the PLN before in the OpenCog Classic. So it has been ported to MeTTa, and pretty much everything is the same. So we will check the conditional probability consistency of the two relationships, like for the PQ and QR. And if they do have, then we will check whether Q, which is a middle, the PQ and QR, whether that is less than, it should not, I mean, if it is 1, since we are dividing by 1 minus the value here, then we have to make sure that we didn't get a 0 value here for the 0 division error. So otherwise we will do the formula here. And once these preconditions are met, we will be able to get the deduction strength formula. And we will be using that for generating the truth value for the P implies R, which is our conclusion. And we will do so by using this formula. And like the Intel version, we do have a couple more, like a match version, like Neil showed for the implementation, for the implication deduction, implication rule. So we do have the same. Let me test the Intel version here. Let's say we have PQR with a certain truth value and P implies Q and Q implies R. Then we will use the lit here just to be able to match the predefined values here. And once we have declared PQR, PQ, and QR as a variable here, to be able to get what is defined here as a null base, then we will be able to do the pattern matching here and use the Intel sign here just to match such a pattern and get a result. So this result will be using the Intel version of the deduction rule. So I can run it. So this will generate the P implies R, and it will also generate the truth value for the P implies R based on the evidence we have here for P, Q, R and their relationship. And the match function, the match version, like Neil mentioned, is the same except using the pattern matcher. I will just go over it and show you this simple example that we have by using the implication direct introduction match rule and the deduction match. We are trying to see that if we have an implication direct introduction rule, and which will get us, let's say, for example, P implies Q, then, and if we already have Q implies R in Atomspace, then we can actually apply the deduction match and get Q implies R without, I mean, just by using the results of the implication direct introduction. So once we can look for PQ and with an empty evidence, I mean, an empty set of evidences here, we can assume that P implies Q have a relationship here. And with Q implies R being inside the atom space, we can actually take the output of the implication direct interaction here and having a baseline, like a knowledge base inside the atom space, like what's P, what's Q, and what's R in their truth value. Then with given Q and R here as with their relationship with implication link, then we can say that if we apply the IDI being here implication direct introduction rule, if we induce that and have the result as a single variable here, which can be P implies Q, right? And we do the match here. This match is actually the deduction match, so it's exactly the same. So deduction match means exactly like the pattern matching in OpenCog Classic. Like if we have P, Q, and R, and Q implies R, as well as P implies Q. Here, the P implies Q will be from the IDI induction here, because the implication direct introduction will be able to get P implies Q because we have the knowledge base inside the atom space. So once we have that, we can conclude that P implies R, and we can formulate the truth value for the conclusion using the deduction formula here. For certain reasons, this IDI induction right at the moment generates more than P implies Q, because P implies Q will have of different versions with different truth value options, and with that being more than one result at the moment, it is not giving me a result. Like it will take a while to execute it and to generate a result. So since we don't have much time, I will not be going through that. I think I have covered everything I have, I guess.
Okay, thank you, Hedra. So I think we're done with our well, we're done with our presentation. So do we keep the questions for later, or do we take questions now?
Hi, Nell. I'm just going to see if anyone in the room here has got any questions live for you. We haven't had any come in yet on YouTube or across the Zoom. Anyone in the room have any questions? Firstly, a big clap. Thank you so much.
I have a question or a topic or something.
Thank you.
Yeah, for Nil and Hedra. So I think it's really exciting to me to see some AI stuff start to get developed within MeTTa. I mean, it's very, very early stage, but I'm curious how the details are going to work out in terms of the type theoretic possibilities in MeTTa as connected with PLN. So there's probabilistic type systems that Jonathan Worrell has written about and we've talked about. And you of course can have first order, second order, and nth order probabilistic type systems. And I'm wondering how much of the PLN mechanics can somehow be baked into the definition of like higher order probabilistic type systems, and then how that brings us to the relation of probabilistic programming in the conventional sense and probabilistic logic, both of which can be simplified somehow by constructing the type system appropriately. And yeah, any comments or thoughts on that you have would be interesting. And Jonathan, who's in the audience, might have some thoughts to share on that also. Right?
Yeah. Well, that's a heavy question, but right. So in terms of expressing well, properties as type, I mean PLN theorems as type, we already experimented with that, and so in principle, that works. I mean, in Idris, that would work very well. In MeTTa, that should work even better. But as of right now, the problem we have, the blocker, is that we do need something to synthesize the proofs. And so I don't know, like I don't think that MeTTa can do that out of the box, just like it can chain reasoning via evaluation by chaining equality, but relationship. But as far as synthesizing programs that are proofs, I don't think it can do it out of the box, but it would be good if it could, or at least if it has the additional functions and tools to do it. Now, as far as probabilistic programming is concerned, I haven't thought about that actually, but I think it's probably going to play nicely. That's yeah, I don't have a good answer for that, but I have a feeling that it would play quite nicely.
Jonathan, you have any comments on that?
I mean, it will actually overlap a bit with my talk.
That's fine.
It might make sense after my talk.
Okay. So Jonathan says this relates to his talk, which we'll then we'll wait for that. So Hedra, I have a quick question for Hedra as well. So must have been a couple years ago, Hedra, you did some work which I was peripherally involved with on the bio-atom space, and we were making vector embeddings of nodes in the atom space representing things relating to medical patients and genes and so forth. And there was some PLN inference there, right? So we were doing PLN reasoning to build like intentional similarity links between nodes in the atom space. And these intentional similarity links were being used with kernel PCA to make vectors you could then feed into neural net. So how are there any obstacles to doing that in MeTTa? Like what's missing in the MeTTa infrastructure to be able to redo that neural embedding of the atom space?
From what I see right now, I mean, with the current version of MeTTa, I can see that we can do even more than the one we had, because we do have a few more options here, like the pattern matching will not be like we used to, like it will not be generating what the pattern matcher gets as a result into the atom space, which was one thing. And the other thing, I mean, it's pretty much possible to do the exact same thing with, it's on a preliminary stage right now. I might not be able to speak that of MeTTa. I mean, I'm on a preliminary stage right now. So
yeah, I guess I think you have a point though, that some implementation details of the OpenCog classic pattern matcher added some unnecessary inefficiency to it, and that's you're not putting all this cruft into the atom space with the way that is pattern matching. So yeah, that would be an advantage. So
other than that, I mean, I don't see any big obstacle coming through MeTTa. Instead, I see that there is a big opportunity for us to move forward doing such reasoning stuff. Yeah.
Cool, thanks. Yeah, so Mike is digging back into Mike Duncan, who's here in the audience, is digging back into bio-atom space, looking at using PLN to do transfer learning between flies and humans. So like we learn some things about which pathways and genes help flies live a long time. Try to do some intentional reasoning to help guess what genes or pathways would make people live a long time. So that's a sort of different application of intentional similarity and intentional implication. So yeah, we may have more users trying to make this work soon. But yeah, thanks.
You're
So it's Jonathan next, and if you want to introduce Jonathan, I'll introduce Jonathan. We'll say thanks, very big thanks. I'll let him know. And here in the room, our fabulous Dr. Jonathan Worrell on formalizing higher order probabilistic type systems in MeTTa. Thank you very much. One second.
There, I'm gonna check out my slides.
Hey, everybody. I just wanted to let you know that we'll be right back in just a few seconds, like less than a minute. We'll be right back. Just letting everybody know that we're going to be back in just a minute with Dr. Jonathan Worrell and his talk on formalizing higher code probabilistic type systems in MeTTa. Be back super shortly.
Can you hear us?
We hear you great.
Okay, here we go. Thank you, Jonathan.
Okay, so I'm going to talk about formalizing high order probabilistic type systems in MeTTa. Okay, okay. So I'll begin by talking about some general perspectives on high order probabilistic types. Then go into detail about just some background on probabilistic dependent type systems in general. Then go on to second order and higher order distribution types. And then at the end, I'll talk a little bit about some work in progress on infinite order probabilities in MeTTa. So to start with then, so some general perspectives, why do we want to model higher order probabilistic types? So as we were mentioning before then, via the Curry-Howard isomorphism, doing so can allow us to model uncertain knowledge and higher order beliefs. Also, there's the probabilistic programming and Bayesian modeling perspective, where we're automatically incorporating things like higher order priors, meta-learning, and meta-probabilistic programming over types and programs. Also, then there's the potential when we come to thinking about infinite order probabilities for modeling self-reflective reasoning, so in particular self-modifying models. So just to some background in on probabilistic dependent types. So this is work which is actually in the paper at the bottom, which is from the main conference. So this system it's a general system then to model probabilistic dependent types, where we're what I'm calling a probabilistic dependent type system includes dependent types, subtyping, and non-determinism. And we have primitives for these primitives: random, sample, thunk, and distribution type constructor. So these are the syntax and typing rules for the system. And basically the distribution is a type constructor which takes a probabilistic term and turns it into a distribution type, or takes a type and forms the type of distributions over that type. And thunk is a constructor for that distribution type. Sampling takes distributions in a distribution type and allows us to generate probabilistic terms in the underlying type. And random is a constructor by which we can build up such probabilistic terms. So this is just generally how that looks in MeTTa. And it's pretty much we can just take these rules and turn them into MeTTa expressions, pretty much. And then this is how we then model a simple Bernoulli distribution in using these constructors. So there's a few points I just put to note then regarding the formulation. So so union types I've simulated using this non-deterministic typing here. So effectively, by letting us say that union T1 and T2 is either equal to T1 or T2, we get we can build a supertype over those two. And thunking here uses the MeTTa atom type, which avoids MeTTa evaluating the sub-expression. So it just holds at a particular expression. And the other thing then in this Bernoulli example to note is that implicitly we can take the non-deterministic semantics, which just where we have a list of all the return values, as implicitly representing implicitly representing this via a multiset. But here it's not actually a multiset, but we have the return values in proportion to the degree that we would sample them in the distribution that it's returning. So here implicitly random is well, Bernoulli here is implicitly a fair coin toss. So we return true and false in the proportion 50% each. And so we can think of sampling from those return values as the output of the program. So this next example then just does a similar kind of thing, but now we're talking about colors instead of Boolean values. So this is just a type with red, green, and blue, and we form this color distribution over those three values. And so this expression for the color distribution first chooses randomly between red and green or blue, and then it randomly chooses between green and blue. So when we sample in MeTTa from this, and it returns to us this list red, green, red, blue, implicitly we can think of that as a multiset, which is representing the multinomial distribution where red has probability 0.5 and the other two have probability 0.25. So these are two simple examples. Here's an example then where we now introduce a dependent function. So we have this f function which takes, f can take true or false, and if it takes a Boolean. So if it takes true, it returns a sample from a Bernoulli distribution. If it takes false, it returns a sample from a color distribution. So f has a dependent type, which is written type theoretically like so. So it's depending on what we get, will either return a Boolean or a color. We can then pass the output of this function f into a this f then is used to build a hybrid distribution over bools and colors. Bools and colors, which are here typed to the union type Boolean, Boolean and or Boolean or color. And then so if we sample from this, hybrid distribution, we get this set of values here. And we can then feed that into what I've written as the hybrid permutation, where we apply not to the Boolean values and a color permutation to the color values. The thing to note on this example here is that the multiset that this returns actually, so it returns this multiset false, true, and then green, blue, green, reds. So it's permuted the colors. But implicitly, we actually want this f to, so if this hybrid distribution applies f to some, really the f, really we should have, really the true and the false should be weighted as half of the probability mass, and the rest of the color should be half the probability mass. So implicitly, we have to think of bracketing this multiset that has been returned. But with that proviso, we can still think of that multiset as being a representation of the distribution. So this, that's just an introduction to probabilistic dependent types. So now I'll say a bit about where, if we want to build higher order probabilistic types. So higher order distribution types can be built by recursive clunking. So for instance, if we have the type pool contains true or false, the type distribution over bools contains all Bernoulli distributions. The type distribution over bools contains all beta distributions and other distributions over Bernoulli distributions. So and obviously we can keep forming recursively distributions over distributions. So as a very simple example which shows how we are basically doing recursive clunking is just to think of constructing a delta distribution over a delta distribution. So trivial is going to be this distribution. Trivial has the type thunk, true. So if we sample this trivial distribution twice, we just get a value true. If we sample it once, we get a delta distribution over true. And the term itself just represents a delta distribution over that delta distribution. And so each of those samples just removes one of the thunks from the term itself. So this is applying this kind of construction then to build up a second order color distribution in MeTTa. So we had the distribution over colors, which we just had in the previous example. So we can turn that now into a permuted distribution. So if we just thunk that color permutation, we turn that into a new distribution over colors, which now has green more highly weighted than the other two. And then we can then form a second order color distribution by forming a term which chooses randomly between our original color distribution and
Yeah,
the
I'm not sure what
permuted
that
one.
means.
So he is
Right, everybody can, so how do I do something or not? Okay.
Lisa, we can hear you. It seems like it's.
So we have the distribution then chooses one of those distributions randomly, but then halts the computation. So it doesn't go on to sample from that distribution. It just returns a token which says either the original or the permuted distribution. If we flatten that color distribution, then we can just draw a sample. We can just resample it at that further stage, and we then generate either a color or a bow. So this is what I'm calling it. So you can see here for the flattened distribution, we have two sample statements here. So what this looks like then when we ask MeTTa to evaluate these things is, so this is just to note this, when we ask it to sample the second order color distribution, it returns these sort of large expressions, some random and so on, or some cold and so on. Really, these random expressions are just equivalent to they're beta equivalent to coldest and coldest permuted. So it's just, I mean, you could summarize those terms by those two terms. So it's returned what we wanted it to, basically. So if we then sample from the flattened color distribution, we then get the multi-set which arranges those colors in proportion to what you would get from sampling those two distributions. And here it really is they're all incorrect. So we could literally just use that as an urn to take colors out, which would correspond to the true distribution. So for the this is then just applying the same thing to the hybrids color Boolean example. And here, so we can form a hybrid permuted distribution by taking our original hybrid distribution and forming a second order hybrid distribution, which so the hybrid permuted one just applies this hybrid permutation, which either uses the not permutation or the color permutation to apply to the outputs. And then similarly, we can form a second order distribution over the hybrid types. We can again flatten that distribution. And then again, if we try sampling, we get these large expressions for the two when we sample the second order distribution, but they're again equivalent to they're equivalent to hybridist and hybridist permuted. And if we flatten it, we then get this multi-set again, which here again we have to imagine brackets around it to get the correct weighting. So there's a few general issues then I just wanted to go through with in terms of higher order probabilistic types in general in the setup here then. So there's in the probabilistic dependent type system I've outlined then, there's a difference between the I mentioned this a little bit before. There's a difference between the term random, true and false, whose type is bool. It's a probabilistic term of type bool, versus the term thonk random, true false, whose type is a distribution over the bools. And so here the former probabilistic term exhibits non-deterministic behavior on reduction, while the latter, which is what we call Bernoulli, represents or names that behavior, but is itself in normal form already. So reduction doesn't do anything to this thonk term, so it can serve as a name for the Bernoulli distribution, whereas that first term gets reduced further by the reduction by the evaluation semantics. So that's just the first thing to know. And this kind of setup then may be given semantics based on what's called the Dewey monad in category theory. And this is similar to an approach that was taken by Sutton and Frank Woods in a paper from 2016. So this bottom part basically recapitulates what I said. The importance of evaluation semantics. We require that sub-expressions here in this system, we're requiring that sub-expressions are not reduced under a trunk or a lambda. So I mean, in traditional lambda calculus, it depends on the flavor, but there's some forms in which you don't make reductions under a lambda. But part of the point is we can enforce it using MeTTa's atom type. So we can make these internally within MeTTa itself. We can put these rules in by the way that we type things. So that's the part on. So now I'm going to go on to talk about infinite order probabilities. So this can be seen as an extension of the higher order probabilities part. So infinite order probability distributions can be defined as circularly as distributions over infinite probability distributions. So this is using Ben's definition from 2008. So if we let S be a set, then for all f in S, f is going to be a function from S to 0, the interval 0, 1, such that the values sum to 1. So for this formulation, for each f in S, it is an IPDF, and we thus require it to be a solution to this set equation, where we can see that we have S on both the right and the left-hand side of the equation. So S has to be a non-well-founded set, since it contains subsets of the product of itself with the unit integral. And so it can be shown that by the solution lemma, such a set exists in Axel's non-well-founded set theory. So I'll just say briefly, give an indication of the sort of semantics in Axel's set theory that this gives. So non-well-founded sets can be modeled in Axel's theory, which replaces the axiom of foundation in ZFC with the axiom of anti-foundation. And this says that it should say every graph has a unique decoration using non-well-founded sets. And we're particularly interested in accessible pointed graphs in this context, which are fully connected graphs such that each node can be reached from each other nodes, and which have a particular element selected as a point. So such a graph could be, for instance, this graph with A selected. And the decorations that we're interested in are putting sets at these points in locations in the graph. And the kinds of decorations we can use then here are, for instance, if we say that A is the set such that it includes this subset which has a complex relationship of including itself within its various subsets, and this other subset which includes a subset which includes itself, that describes what set has to live at that node in the diagram. And then we can similarly find solutions to non-well-founded sets which must lie at these other points in the diagram. And then so further then, two APGs are equivalent if they can bisimulate each other. So this is the basis of non-well-founded set theory semantics. But we're now interested in how we can simulate this in type theory. So non-well-founded sets can be modeled in type theory by type systems which allow an arbitrary typing relations here. So in particular, there are systems called pure type systems which offer such a system. And here we can, for instance, say that, so here I've written down, A is of type B, A is also of type D, B is of type A, C is of type B, C is of type A, and D is of type C. So these typing relations mimic the structure of this APG. So further, we're interested now also in introducing probabilistic terms into this framework. So for instance, we can introduce probabilistic terms fairly directly into a PTS. For instance, if we set the term little a to randomly sample between B and C, then effectively we're making it, since B and C are members of the type A, we can form this term A, which randomly puts these weights on the APG. Similarly, the term little b randomly samples between A and C, which belong to type B itself. So we can form probabilistic terms in a PTS by using random constructions, and then further we can so a convenient thing then to in terms of is then to think of these as that all of these terms as members. Well, so they're both terms and types here. Well, these are terms. These are the little a, b, c, and d are probabilistic terms. Capital A, B, C, and D are both terms and types here. But we can see that if we form the union type of A, B, C, and D, then all these probabilistic terms are going to live in that union type. So now I'll go on to say then how we can use that to form to convert this into a model, an IPDF model in type theory. So we can do this by by considering the distribution type constructor as a functor. So if we've got the we've been talking about how we can form distribution types over a given type. But if we now consider what is the fixed point of that distribution functor, so, and we call this F. So this has to be a type which is its own distribution type. So if we find this fixed point of the distribution functor, then to form a type of infinite order probability distributions, we require the greatest fixed point of this distribution functor. So like I was saying, hence we have F is equal to its own distribution type, and for all F, little f's in F, we can sample from F, and it's still a member of capital F, and we can also thump that little f, and it remains a distribution within capital F. So capital F is a type whose elements are distributions over F's. Over F, so i.e. that's a translation into type theory of the definition of an infinite order distribution made out of sets that we had earlier. So for particular APG, then we can consider the subtype. A subtype within this fixed point, which just models the IPDFs that you can build over a given graph. So that's what I'm meaning by this line here. This is a subtype of all IPDFs that we can build over the graph A, B, C, D. So now we can actually fairly directly translate this into MeTTa, surprisingly. And so this is actually what I've done here. So taking this graph here, I just used this is just summarizing the type theory formulation that I've just written over the last few slides, and then just literally translating it into MeTTa here. So we just translate the typing relations, group this all together as a supertype. We then form these random terms within that pure type system. And then we can take those terms and turn them into an IPDF by just adding a choice function, which takes a type with choice function, which I've called here G, and that just takes a type within this within this graph, say A, and gives us back the corresponding IPDF which goes with that type, a little a prime. So it just provides a choice function which chooses chooses an IPDF to go with each of the points in this graph. And I mean, so given this choice function, we can then build a set of terms, these A primes, which represents the IPDF which lives at that point in the diagram. In other words, if it was a pointed APG, then for A we would use A prime here, and for B prime, and so on. So these give us a little. So the other thing to note is this is actually what in Ben's paper is called a mean indexed PDF. So it's a particular kind of PDF. But I mean, so this particular construction using the choice function.
You can do it on for
Yes, exactly. And I think they all will be. I mean, they all will be typed to this fixed point. This fixed point type, but they will require more complicated constructions to construct. But this is one way of I mean, this particular constructions forms MIPDFs is particular. But I think more general constructions are possible in MeTTa as well. It's not limited to this construction. But so having made this construction, then we can just test out a few things in MeTTa then. So we can literally sample from these IPDFs. So for instance, if we sample from A prime, we get as we would expect. So we know that if we sample from, we can see on the diagram, we should get a collection of B's and C's. And that's what happens here. So we get, and moreover, these are in the proportion 50-50, as we would expect, because those are the weights on the graph. So so then if we try to sample from that sample, so double sample from A, we can see from the graph we should get all types excluding B, which is what happens when we write it, when we ask MeTTa to evaluate it, and that's forming some complicated distribution over those A, C, and D, and then we can keep going and keep resampling from those terms, and we gradually get. I mean, I didn't actually write out. I mean, you can get MeTTa to evaluate it, and it returns a long several pages of A's, B's, C's, and D's. But the point is that as you keep adding sample statements, this should converge to the steady state distribution of this MIPDF. So the proportion of A's, B's, and C's that MeTTa returns should converge to that distribution. So this is just another example of sampling from C, which here doesn't generate quite such long statements, but C deterministically goes to D. So you only get D's in the first return statement. D's only would go to A's, so 2 sample statement just gets you lots of A's. But then if you do 3 sample statements, you start getting lots of B's and C's, because then A samples to B and C. So those are 2 examples. But you can also ask MeTTa then to evaluate, to do type checking on various terms as well, which seem to come out as desired. So if we ask MeTTa what is the type of A, it says that it belongs to type, but it also belongs to types B and D as we expect. If we ask it what's the type of the distribution over the distribution of the fixed points, it says it's the fixed point itself. So that's as it should be. If we ask it to say what's the type of this non-deterministic term living at A, then it says it's A, as it should be, because A lives in A, so it has to be of type A. But then if we ask it what is the type of the IPDF labeled by that A, then it says it belongs to the fixed point type, which is as it should be, because we've just constructed it using the MIPDF construction. So I'll just conclude then. So I've introduced several variations of higher order type systems. So we started with a probabilistic dependent type system, which had non-determinism, subtyping, and higher order probability. Well, I suppose we started, well, it automatically includes higher order probability in the original system, but I sort of separated it out into the first and lower order and then the higher order parts. Then I talked a bit about pure type systems, which are basically non-well-founded deterministic type systems. And so the final system then, which has the infinite order probabilities, is effectively so it's effectively a PDTS, a pure probabilistic dependent type system with non-well-founded types, which allows you to formulate infinite order distributions. So this relates to the work in the main conference on meta-probabilistic programming, which I'll give a presentation about tomorrow. And I put these meta examples then on the in the GitHub repository for both the PDTS system and the system with infinite order probabilities as well. If there's any questions, I'd be happy to take them.
Thank you very much, Jonathan. Right. Do we have any questions for Jonathan in the room? We have some online. Doug, but if you come up and that's really helpful, then they can hear you online and see you. Thank you.
So we have non-determinism here. How does that affect the type check? Is it a small search that happens?
I mean, I suppose I'm building all of this on top of the current meta implementations. So I'd imagine there's going to come some point where we ask it a type of something that it can't evaluate. Yeah. But so far, I mean, for many of these terms, it seems to be able to find the correct type. So yes, I suppose I'm not sure at what point it's going to.
Right. Yeah. So it's a work in progress. It definitely is able to do the type check despite non-determinism, which is
yes.
But yeah. Okay. Good. Yeah.
Yeah, I wanted to make since we got to the point of infinite order probability distributions, I wanted to make a quick comment for the audience on why these things might be interesting, apart from being really fun general mathematical tools. I mean, I remember, I think I presented the idea first at a conference in China, which was one of the talks I've given where I realized that absolutely zero people in the audience, except possibly myself, had any idea what the fuck I was talking about. But on the other hand, if you know non-well-founded set theory, it's actually pretty trivial. It's just like taking Axel's theory of sets to contain themselves as elements and think, well, probability is set theory, right? So you can do that. But where the reason I thought of introducing that in an AI context was Barwise's theory of situation semantics, which is from a sort of abandoned thread of cognitive science. But if you ever look at the book The Liar by Barwise and Etchenergy, which is from the 80s or 90s, it's a very elegant explanation of why non-well-founded sets are relevant to cognitive science and thinking. And a simple example is, say something like, well, I know that you know that I know that you know that I know that you know that I know that you know. So I know I know Jonathan knows this. Jonathan knows that I know that. And this sort of recursive knowledge between people, actually, a simple way to model it is using a non-well-founded set. Like I know A, which is that Jonathan knows B, but B is that Jonathan knows A, and so forth. So Barwise goes through and actually, in a bunch of books from the 80s or 90s or way back, he goes through various social situations and basic mutual construction of social knowledge and models that using these non-well-founded systems. So he's doing using crisp logic, but of course, all you have to say is like, I know that you probably know this, and you know that I probably know that, or I doubt you know that I probably know this. And then this sort of recursive knowledge among a community is naturally modeled as uncertain non-well-founded sets, which basically brings you to infinite order probability streams. I mean, you could also model it more trivially and less practically. Is like instead of this sentence is false, like this sentence is probably false, right? And then again, you have something that needs an infinite order distribution. But the modeling of recursive social knowledge is perhaps the sweet spot where this is actually in some ways the simplest sort of math to use to describe that. So I mean, I think seriously, if you had a sort of DSL in MeTTa for social psychology modeling, which actually is a useful thing, that could actually use this sort of infinite order probability type system. So it's not. I mean, he's focusing understandably on the math of it, and it's amazing to have it worked out in an actual interpreter. But there's also a cognitive angle. So I just wanted to highlight that.
No, I think also I mentioned the beliefs.
Yeah. That's right. I believe that infinite order probabilities are useful, right? So yeah, right. So there, yes, and this ties in with consciousness, which I brought up in my talk in the beginning, with sort of raw consciousness that everything in the universe may have is one thing, but the type of consciousness that humans have, that worms have much less of, and dogs maybe have a little of, and rocks have very little of. This is like abstract reflective consciousness. It's like modeling your own self, and then your self model is part of yourself. You have a sort of fractal aspect there. And again, this sort of infinite order probability is perhaps the simplest way to model uncertain, reflective, recursive self-knowledge like that. And if you're not completely self-delusory, most of your self-knowledge is highly uncertain, right?
That's strange loops.
Yeah, Douglas Hofstadter's work on strange loops, going back to Goertzel in his subsequent work. Again, he didn't use this math to model it, but it actually provides a more elegant way to model a lot of the things Hofstadter was talking about. That's the first book of AI research I ever read. I think it was like 12 years old or something. It's still a brilliant one.
Fantastic. I've got a couple of questions for you online as well. Thank you. So the first one is, in a real application, how difficult is it to determine these probabilities appropriately, or the evidence for a proposition?
I mean, I think there's I think in terms of say learning a model which uses this framework. I mean, it's a little bit like if you're using non-parametric Bayesian models, where you have infinite order models which you fit to data, and typically you use the infinite model as an approximation to a large finite model. Only you can flexibly fit the degree of at what order the you can use it to effectively find the size of the finite order model that you want to fit, which I suppose in language there's always in principle our language contains an infinite number of statements because we can recursively embed statements, but we have a recursion limit in our base, so effectively we can effectively the infinite order model serves as an approximation to an infinite number of finite models in that sense.
Yeah, I mean, if you tried to bottom that out in terms of like constructive non-standard analysis or something, you basically an infinite model just becomes a model that's so big I can't conceive how big it is, and you can just, it doesn't have to be an actual infinity. It could be a potential infinity, which is bigger than you can deal with. And the crux of it is that dealing with the infinite model can be more computationally efficient than trying to deal with the finite model of some specific order. So just saying it's some really big order, big enough, I don't need to worry about how big, that saves you computation time over saying it's a specific n. And then, I mean, philosophically, that's not really any different than using calculus and differential equations to figure out things about finite precision measurements in physics. Like, why do we use differential equations instead of difference equations? Because keeping track of all those error terms is a pain in the butt. So you just assume the error terms are small enough, you don't need to worry about it, right? It's really a similar sort of thing.
And also, I mean, say in evolutionary models, I mean, there are fixed points that systems will converge on. And I mean, it may be that no system fully converges on that fixed point, but there are many systems which approximate it to various degrees. And I mean, in that sense, the infinite system which represents a fixed point can be more informative than having lots of approximations to it in terms of the overall dynamics.
Again, it's a computational resource thing, right? Because all the specific things that are almost at the fixed point will be a big mess to keep track of them, and you can't do it. Right?
Okay, thank you. And just one more question for Jonathan. How sensitive are the inferences to incorrectly set probabilities? If it is uncertain what the correct values are for probabilities, is this logic still usable, i.e. MeTTa, in MeTTa?
If it is uncertain what the correct values are for the probabilities. I suppose this actually ties in a little bit maybe with a PLN relationship, that if there are uncertainties in probabilities, then I mean that's what we're actually talking about when we're talking about higher order probabilities. We're talking about distributions over probabilities themselves. So it's I mean I think a lot of the PLN models will fit into this kind of framework, because I mean essentially I suppose there are various, it depends. I think we can model PLN within this framework. I think PLN can be, I think it can give rise to different kinds of probabilistic models, but one possible way is to fit these higher order distributions explicitly to model higher order knowledge.
The final contribution here, I've thought of a new buzzword for your work. So these non-well-founded sets, we've gone beyond deep learning. It's bottomless learning. Yeah, never bottoms out.
All right, thank you. Bottomless learning, that is just perfect. Now we're talking my language. All right, thank you very much indeed, Jonathan. Let's give him a big clap. All right, so we've got two more talks to come today. Next one I'm really excited by. Adam van der Vorst is here in the room. And he's going to talk to us about, for every job, the right tool, Hyperon DSLs. Thank you.
When we're presenting, there's always like something blocking the screen. Is that unavoidable? There was the top menu and then a
text.
tag.
Okay,
Yeah.
yes.
That way.
We always try.
It's covering parts of the slides.
So that menu is strong down. Made floating menu control. There we go. Adam, over to you. Thank you.
Thank you very much. So I will be talking about, I will be doing a high-level talk today about the.
We need you to talk louder if you can,
Yes.
please. Thank you.
I will be doing a high-level talk about DSLs and MeTTa, so domain-specific languages. And this will go beyond what you typically conceive as domain-specific languages, because MeTTa is a very small assembly language almost. So let's start bigger. Right, and so we will build languages on top of this very small but expressive core, as Jonathan has just elaborated on, actually. I will try to also insert some examples, especially if people are interested in specific parts of it that you can run, that you can play with. Again, as the MeTTa examples effort is continuous. And then this is also a collaboration. This is a very new system, Hyperon, and building out one language is hard. Building out a whole DSL hierarchy of languages building on top of each other, specializing into different domains, that's very hard, and that will need contributions. So lastly, this talk will be like an ode to technology and how far we have come and how we should integrate these new achievements into our future systems, including the Hyperon DSLs. So quickly about me, I've been doing mostly machine learning, engineering for various clients. I've done informatics research, especially in graph generalizations, graph rewriting, evolutionary systems built on graphs. And I've also done some work on automation, so taking large pipelines of old school software and compacting these down, modernizing these into something understandable, something maintainable. And so currently I'm working on Hyperon, specifically on DSL's efforts and the accompanying work on MeTTa itself and on an editor system. I'm also doing work on a brain-computer interface application for the University of San Francisco, and this is actually more relevant than what I would have thought 6 months ago, in the sense that you're building an operating system almost from scratch. You're not just building a language or not something to solve one problem, but you're making a tool that makes it easy to solve all these kinds of problems. I'm also doing research in what's called incremental computing. So instead of running a program eagerly front to back, you are integrating changes as they come. And this will also play a role later on. After a talk, you can always ask me questions about it, talk to me about crazy graph problems, AI safety, technical alignments, and programming synthesis, generating solvers. All right. So we'll start by covering like some AGI software needs, what it takes to, depending on what AGI will look like, what it will take software-wise to get there, what paradigms do we need. Then we will cover what software we already have and and how we can use this to reduce complexity. And very importantly, for such, we want AGI to be, why do we want AGI? Because they are powerful systems. If they are powerful systems, we also want to be able to trust them. And so I will be covering some of that too. Not towards the classical alignment, but more towards the trust in software. And then finally, I will be covering some concrete efforts, yeah, we will go from there, see what the questions are and what's the interesting parts are. So the first scenario is, what if AGI is end-to-end deep learning? It's interactions with worlds as inputs and its interactions in the world as an output. It may seem that there is not much software development going on here, but the opposite is true. Like training these models and having a setup that can integrate the experiences is very non-trivial. The deployments of larger models has been a bottleneck to and a mode for companies, for startups, how we can create an application, a practical application from something that's fundamentally pretty simple, like a universal function approximator or a transformer network. Then if we have this system, we still have some integrations, not for very little because it's end-to-end with world interaction, but you still want to do things like monitoring, and you want to do things like give it tools to work with and reduce the bandwidth necessary. You don't want the typical sci-fi computers, robots typing on a classical keyboard. No, you still want some level of integration with software. And for this, probabilistic programming is really interesting because that allows you to model these probabilistic networks, intrinsically probabilistic networks, into the hard software worlds that's not used to think in probabilities. This thing I already covered a little bit. Out of distribution behavior is also a really important one. Can we take this deep learning system and put it in another environment where we can stretch the laws of physics, stretch the scenarios that we normally won't be able to create? An example of this for a computer vision network would be to take Photoshop and take a scenario that's unlikely to happen, like a very large bird, like a 5-meter high bird, and see if it still recognizes this as a bird. And as people have shown with this technique, this is not always the case. So out of distribution behavior, lots of tooling that goes into it. And final part is with the end-to-end deep learning scenario is inspection. How can we take this opaque trillion weights model and understands why it has the probability outputs that it has and takes the actions that it does? So this will be analyzing the attention mechanisms that it has. It will be analyzing which data points contributed to the weights in the network that trigger in certain events. And it will be very hard. This is an unsolved problem. If people are interested into this, I highly recommend Potopav and Chris Bolles' work on this. So, second scenario, MeTTa algorithms. This is not an end-to-end approach. You basically have a running system, like evolutionary research, like an automatic assembly of services. like a meta learning algorithm, for example, a deep learning algorithm spitting out other deep neural networks, hierarchical deep learning networks. It's not very hard to see here that this requires a way to work with probability, with rewards and credit assignments. And in checking if things are meta, that means there are things being generated. How do we check this volume that's being generated? Can we ensure this, for example, by construction, that we are evolving only code of programs that are guaranteed to stay within memory bands, for example? Another thing that complicates this is the distributed nature of these large training efforts. As I mentioned before, for certain companies, this is their mode. This is what they hold dear in their revenue creation, not the idea, but the execution of distributing this over many servers. And then the final part is alignments. Alignments in the sense of making this system do what you want it to do. It's really hard when you're working with mass optimization or with optimizers over optimizers. Even if your high-level optimizer is aligned, it doesn't mean that your lower-level optimizers are aligned. And actually, a good point to illustrate this is that we are, in some sense, as humans optimizers, creating other optimizers. If we are creating meta optimizer, then it's another level. So that's hard to get aligned. Next one is the Neural-Symbolic scenario. I've taken quite a small fraction out of this scenario, namely where you have your execution is mostly done by something like a neural network, a value network, and you can do some Monte Carlo tree search or whatever, and you're augmenting this approach with hard data. This can be existing data sets. This can be querying the internet. This can be human constructed knowledge. And to work with this amount of data, our current programming languages aren't built to do this. If you have a CSV file, you can have a very type-safe programming language, but when you're reading in, you enter the world where things can go wrong, and when you're duplicating things. There are some efforts, for example, with the CSV file, to take the headers of the CSV file and actually look at this during compile time. So you can safely reference the different columns at compile time. And this is checked for you. And when we talk about AGI systems, we are also talking about long-running systems. So we want to do this iteratively. We want to integrate some files, integrate some data, and check this as we go. So I will come back to this, but gone are the times that we have a compile time and a runtime. We are going to have a way more iterative way of development. And the last scenario is an assembly of existing techniques. This means taking the software we have developed for tackling specific problems and assembling this into a whole that can solve more than its parts. Taking a planner specialized for shipments and applying this to a new area so we can feed in our computer vision system and focus a camera on the lesser or the ambiguous part of an image. Things like this. What's very hard about this is that many of the tools we build today are not transparent and don't admit to local reasoning. That means they are not very composable, and when they are very hard to understand when they are composed. We also will need a way to analyze dependencies. If we depend on some piece of software, can we really trust this? Can our ecosystem provide a credible contribution? So that's the first part of the talk. I recommend, like, if there are any questions now, especially in the audience, please let me get back to it now. That will be easier than going at the end of the talk. Yes.
Could you say more about how you solve the alignment problem?
Yes. The alignment problem, contrary to popular belief, or within the alignment community, I believe this will somewhat depend on the architecture that we go for. That means that if we are in a certain scenario, for example, the end-to-end deep learning scenario, that this will be different fundamentally so from the very last slides, the assembly of existing techniques. Because while theoretically, for example, a problem is the orthogonality thesis and how we can develop a smart system, but have it pursue misaligned and stupid goals. But if we are in a scenario where we are applying meta algorithms, we are actually selecting in a similar way than we are selected as humans through evolution. And this, in my belief, will rule out some of the more alien belief or orthogonalities you could see. So to add a final thought to the alignment question, I think the transparency from bottom to top will be very important, and I will try to cover that later on too. If there's any other question. So how do we develop features? How do we work on a novel code base these days? There are what we call smart coding tools. An example of this that's quoted, especially in recent days, is models like the OpenAI Codex. These are large language models that are trained on code instead of natural language. There are definitely problems with this, and I can go into them if there is interest. But what they do is they provide a certain primer over the space of possible programs, and whether or not we use this as a policy, I will forego. But this is very useful even in program synthesis as a directional guide, a statistical guide over a firm inference algorithm. Fuzzy search. I heard someone say at this conference, I couldn't learn to program Haskell if I hadn't had Google, sorry, which is a fuzzy lookup for definitions, where you can search for a very specific problem you have. I want something from strings to strings to strings, and see what the more generic functions are that you can compose to achieve this behavior. Elm has something similar, and so do some other programming languages. The next part is specification and data-based program synthesis. This means that you are not taking a simple set of requirements or data, but you're combining those. You're saying, oh, here are some easy examples that it should do, almost as documentation for yourself. And you can specify some behaviors you want to have valid no matter what. For example, oh, you can this lock does always have to be freed, or well, these things always have to compose in this specific way. And combining these easy examples with the limiting laws creates very interesting program synthesis solutions. The last item here is content to address and name invariance program storage processing. I can't stress this enough. This is talking about the semantics and seeing that a name change doesn't break things. This coming from having worked with this for the past couple of months, it almost feels weird to say that a name change could break things in some scenarios. But it goes beyond that. For example, if you're integrating code from multiple parties, you don't have to deal with binary changes, because your content is actually hashed and referenced based on that. So no version discrepancies there. Program analysis is another thing we've greatly improved on in the last 10 years. If you look at projects like MeTTa or Facebook's ISA, they take a language that's incredibly unstructured, like Python, and doesn't admit standards out of the box to much analysis at all. It doesn't have type checking, and it applies some state-of-the-art control flow analysis, and it checks that resources aren't leaked to places where they should not be leaked. Next one is runtime verification. This means that you admit that you can't control your program completely, or there are some dynamics you're creating. This could be looking up in a database, or in MeTTa, this happens constantly. You have a very small set of very powerful combinators, and with runtime verification, you're checking that these admit to some criteria, some sanity checks that you may not be able to prove over this expressive language, but you can check them at runtime. And then the last one is provable spec abide. So if you have a language specification, you can actually prove that your implementation abides to this specification, which has led to numerous bugs in, for example, the Rust programming language, where certain web frameworks were using parts of the language following spec, but the actual implementation differs. Iris is another example that goes the other way around. Please check the links or check the name if you're interested in that. All right. High-level code architecturing is mostly still a human task. A human task in the sense that it's mostly in our minds, it's in how we collaborate with people. It's not something that's formally set, and it's something that we still want to have a lot of dynamical. We want this to be free, and we want people in this game. but we can also use tools on top of this. The simplest example would be Gyra, but structured references is also a very interesting one for this. Think about documentation, but taken to the next level. If I can actually, I'm not sure if I can open it here, but if someone's interested in that, definitely look at OneLab. Great example. And then code structures. Everyone knows like UML diagrams. Well, we can take this to the next level. We can architect codes based on like the functionality, the high level functionality and how things interact with each other. Visual Paradigm has some great examples of projects that are transformed by that. Right, I think lastly, no, almost lastly, in this part is cloud deployments. I touched about this plenty of times at the beginning, but deep learning, it's all about how you can scale. Keras Tuner allows you to run a architecture search, that search for the best architecture to solve, for example, a computer vision program, and runs it in the clouds with 100 different instances, all training a model and doing a tournament search, for example, searching for the best solution. Distributed databases takes a lot of work off your shoulders and scales amazingly. Ray is a very modern framework for parallel processing. And then Pegasus is another one for specifically for graph processing. Trillions of edges processed over hundreds of machines. Well, that's beautiful if you can use that out of the box. And then lastly is easy development. How can we, if this is such a large effort, how can we make it as easy as possible for ourselves to keep working on this code to develop new features? Online evaluation. This is a very simple one, and something I definitely had a bit of trouble with accepting, being used to very low level tools. But it's amazing what you can do with sharing a Google Colab and having anyone at all take a look at your working pipeline without needing any installs. JavaScript is used by some institutes to teach people programming. I am very sure this is not because it's a good language, but because everybody can use this in their browser, have immediate feedback. Study typing and type holes. This is something that people coming from some languages are used to. This is great. If you don't know what code should go there, you can ask the compiler, hey, what signature should this be? In some stronger type systems, you can even ask, all right, what combinations or what combinators could satisfy or could be used in this instance, going more towards program synthesis. I want to go to a point where you could even filter the terms you could use by their properties, that you could say, oh, I need something that's constant in computational footprint here, and filter down data structures, for example, based on such criteria. Domain-specific UI integrations is something that programmers don't appreciate, but non-programmers working in code bases, experts very much do appreciate. How can we have a mathematician enter statements or enter like not even proofs, just definitions of large mathematical objects. We have languages such as Lean that approaches in a specific way. And so takes the data science approach where you can see what's the result is for every expression you evaluate, even if that expression evaluates to a map, like a world map, or if it evaluates to a table, you can edit it in place. A helpful compiler is also a large piece of equipment here. I especially think about a Rust compiler that's really teaches you how to code Rust, or if you come from some other language, says, oh, maybe you meant this to do this, which is incredibly helpful. And finally, a good IDE that suggests you which functions you can use, admits to easy refactoring. That can also be really helpful. All right, before I dive any further, any questions? If you don't have questions, that's fine. I'm just giving myself a reference. Right. Enhancing trust. So if we are developing AGI, we better trust our system. One aspect of this is having transparent codes. The code itself being transparent means that you can look at it and imagine what the compiler will generate and what it will do in every situation it is used. This excludes things like ambiguous syntax and code obfuscation, but it also excludes things like using black box pre-compiled libraries that you have no idea without digging through documentation that could be faulty, specs that could be off, if they can be trusted to do what they say they can do. Another more subtle way this can happen is that there are lots of indirections, and while they are all transparent in itself, or mostly transparent because they are stacked so high, it's hard to see through it. A fully comprehensible code base is notably distinct from the previous points in the sense that you can perfectly work on a very large code base like the Linux kernel without understanding more than what you're working. This is beautiful in itself, and it has led to great open source efforts. But for an agentistic system, for a system that takes actions in the world, or will make choices that influence people, we want a fully comprehensible code base. That means you not only understand the code, but you understand what the system will do and how the different components of the code base contribute to this. A more subtle way in which this can fail is that parts are poorly documented, under-maintained, or that the contributors don't have the experience or don't have the weren't contributing to the projects yet when the initial goals were set out or the initial sentiments for creating those modules were there. And thus missing the full view of the code base. The next one is track changes. This means Git code changes. That's great, but also versions saying why things changed. If vision changes, that should not only be reflected in codes. There should also be a resource that people can understand. Oh, no, it makes sense that they dropped this feature or that they are now working on vector embeddings instead of this other thing. Yeah, because the vision changed from this to that. And all applications using that, they can choose to either adapt other software or also take into consideration that vision change. This ran off the title. Provably correct or predictable dynamics. You can't assert, or at least not with our currents, without AGI, I don't think you can assert that your code is provably correct, or an AGI code base is provably correct. I believe we very much need AGI to be able to assert something like that. What we can assert for the pieces that we cannot prove is predictable dynamics. It's understanding invocations of very generic functions or very generic, widely applicable code bits with random other pieces that the planner algorithm or some other algorithm may have come up with, that they are predictable in how they will compose. The keyword here is generative effects. Lastly, this is an open question for me, because honestly, I don't know much about it. That's a reputation system, because many problems in current open source projects are not hard problems, but are soft problems, are problems of the original creators, their vision being misaligned with the boards, or are more subtle problems like, should we accept this contribution? And a reputation system may fit in here to enhance the trust in the overall system, in the overall effort. But if anyone has any thoughts, this is the time before I delve into the last bits. Let's get into some MeTTa, right? MeTTa is surprisingly flexible. It looks a bit like lambda calculus with some REST functions or Python functions mangled into it. But you can get a lot done with it. A few examples that I've worked on, and I will try in this section to especially focus not on what we should do, but on things I can get started, and if people are interested, we could definitely collaborate on. One of these things is adding type classes to a low-level language adds property-based or builds functionality on top of each other to build larger programs. Some programming languages like Haskell are built on this, but many others could support this as a good alternative to object-oriented programming for organizing projects. Another one is recursion schemes. I will briefly at the end delve into some practical examples. What it tries to do is to factor out recursion, because you're working with a probabilistic programming language, or you're working with a very bare bones programming language. Recursion can make things very hard and very inefficient. And the last thing is total functions. Alexey has argued that part of the beauty of MeTTa is not having total functions and have it be extensible to new data structures, new definitions. But total functions can be very handy in certain parts too. So there is we can actually trick MeTTa or use MeTTa to verify functions are total in MeTTa, and yeah, and add this extra level of safety when tackling more complex problems. And actually, I will dive into a recursion scheme example, because I think that will be easier to follow. Imagine you have an expression of plus const variables, and you want to evaluate that expression. Then at the top of the screen, you can see the three lines that take the left-hand side's symbolic structure, the symbolic tree, and admits to one step or one layer execution at the right-hand side. So a plus of two arguments, assuming that these arguments have already been evaluated, will be added together with the plus sign on the right-hand side. And as an example, let's say that we can use value of to give a value to certain symbols. And then we can fold an expression, in this case, the plus var x const 2 const 40 expression, and fold over this expression with the definition we made above. The distinguishing feature here is that nowhere is there a recursive parameter or is there a recursive call exposed. The only thing you're doing is you're saying, how can we map over an expression? How can we evaluate one step of this expression and applying this to a tree like shown on the right. Here is another example, but generating an expression. So say we want to have a times operation, so n times something. What we can do is generate this by doing plus multiple times. And as you can see in the unfold, I'm giving a tuple indicated with a prefix comma, a tuple of 2 in the value representation and 2 in the type theoretical or functional programming notation. And I'm saying I want 2 times 2. So I want an expression plus 2, 2. And you can unfold the seed here of 2 and 2 into plus and something unevaluated 2, and then evaluate that unevaluated thing into 2 again and have the plus 2 and 2. What's nice about this, because this you can easily do with a recursive call too, although I would argue that this is not even easier to think about, is you can compose these. So you can compose the folds and the unfolds into what's called a refold and say, all right, given this way of mapping over an expression, do generate an n times expression and evaluate it at the same time. So here we are taking 3 times 3, and we are generating with the previous definitions of n times n eval expression. We are unfolding this and folding this again to get the results of 3 times 3, namely 9, even though we haven't specified a times operation. So that's a deep dive. But I wanted to highlight one part of using MeTTa flexibly. Another Another surprisingly flexible part of MeTTa is multi-stage program. This is where you take some codes that lives or some information that lives at runtime and use it to generate codes that gets executed later on. So you're using a compiler at runtime. People from the deep neural network guides like instantly recognize, or maybe not instantly recognize this, but use this all the time. They are using Python, a interpreted high-level language, to construct a very optimized kernel with either Einstein notation or with high-level combinators or with pre-made modules or just plainly chaining the operations of matrix multiplication, etc. And this gets compiled into kernels that run on the GPU, that run on the TPU, and all future accelerators. And we can do the same thing in MeTTa. In fact, MeTTa seems to be built for this. You have the intrinsic evaluation capability of the match and the equals, but you also have a system of basically creating syntax trees. And you can create functions, grounded functions that take these syntax trees way easier than you could do in Python and compile them into very efficient codes. I will again do a brief, very brief detail of showing the actual implementation of such a thing, where instead of specifying abstract types like integer, you specify machine types like float64. And you can write an inefficient expression in MeTTa, like how to evaluate a sigmoid function. And simply with the grounded symbol of compile that takes this symbol and compiles it with LLVM to a very self-contained, small optimized piece, and invoke sigmoid, and like that compile function adds the grounded symbol with the right machine code behind it. And then now you can use sigmoid as a normal function and say sigmoid of 3 and get the right results as computed with optimized assembly codes. And notice that we didn't use the equal sign. We just used our custom arrow that represents the arrow used in mathematics to indicate how to compute sigmoids, and then use compile in order to generate the equals definition. All right, so I briefly touched upon evaluation schemes. There are other evaluation schemes that are interesting here. I was especially shocked by how interesting pi calculus is. I don't know if anyone here knows pi calculus. Yeah, Ben knows. So this is ancient and not used very widely, but this works beautifully together with MeTTa in a way. This is process calculus. So you have certain communication channels, and you can listen on a channel and send messages over a channel. And that's basically all you can do. You can do some processing in between by, again, sending things to channels and receiving things from channels. And you can, because it's basically just syntax trees all the way down, you can write pi calculus programs and compile them down into very efficient distributed or using pipes that are not local function invocations, but for example across threads or even across machines. And yeah, that's pretty cool, I think. Jonathan has touched or covered, I should say, probabilistic programming for a while. I will quickly show some lazy evaluation things. Lazy evaluation. So the specifics of this example, I left out for brevity some things, but if you define a function ends on true and false, and you use that function in another construct, then that other construct referencing ends as a function will also be expanded. That means that if you say, oh, well, ends and true form a monoid structure, and you ask for the monoids that this gives you, then it expands out the definition of ends into its different components for true and false. This is not always desirable. This is because the inside-out evaluation of method, but this is easily fixed. What we can do is we can, with the ungrounded symbol, just a plain symbol, lazy ends, we can generate a definition that looks like this. So we get one monoid that uses as an operation lazy ends. What is this? Just an abstract tuple of lazy ends. And then when we need to evaluate this monoid, we can simply add one definition to the local scope, which is if you have a lazy op, and actually this should be even simplified further. Lazy op is equal to op. And then you can evaluate the monoid to all its different pieces. Or likely you don't want to evaluate the monoid in all its different pieces, but the specific operation of it or a specific law. All right. Cool. So that's the flexible metacore. Next is the DSL system. And in the interest of time, I will try and keep this rather compact. But the idea of using a DSL here is to abstract away the implementations I just showed, to abstract away the recursion schemes, the different evaluation schemes. Like if you have pi calculus, you don't want all these things laying around. You want a concrete encapsulation of this that's transparent in how it works, but is pretty to look at, is easy for people to digest. And the other parts is if you're working with something like vector embeddings, you want domains, or I should say something like DNA, you want domain experts to be able to look at these codes and not be scared by the parentheses or be scared by the way that files are loaded in via monads. No, what you want is you want a DSL where the domain experts can use the domain specific language to do their work. What makes this into an interesting and rich environment is the ability to take multiple of these DSLs, like PLM and probabilistic logics, and combine these together into a stronger system. So if you think by the Grace robot, you can come up with 10 different DSLs that all come together to form a natural formulation of the very complex underlying systems, or complicated, I should say, systems underneath. And maybe I should elaborate this quote real quick. So to interact with an AGI system is to interact with like all people from different domains at once. An AGI system will be general, and we will need experts to be able to verify its work and to be able to collaborate on designing spacecrafts, cancer solutions, whatever we want to use AGI for. So we will need non-programmers to tune in on this story. Okay. Last bit is about an editor, executor, and explorer. Explorability is very important for any language. And especially if you decide to create a new language for some reason, then it should be at least very easy to get started with. So you should be able to share your codes, click one button, get a shareable link, and send it to a friend that's interested in trying designs. Send it to experts to whom you want to ask a question. And you want to have live examples, have people play around with these different formulations. If you have some computer vision network, you want people to be able to click a link, see some domain-specific computer vision codes, and be able to edit it and see with their webcam the results live of what they are doing. This is possible now. We should be doing this. Next thing is accessibility. The original Atomspace, although a great piece of software, is not easy to install. It took me many hours the first time I tried it, and on a newer system, it took me many hours again. So we should have this no setup, no system restrictions. DSL codes should expand into MeTTa, not replace MeTTa. So we built on top of things. And with an editor, we could write these DSLs as if they are native, as if they are the language we are supposed to code in. And for space age developments, I would close out on making it interactive, type-driven, data-driven. Okay. So we want to create a wide and deep DSL environment, make it easy to write domain-specific codes using the experts, using the insights from biology, using the insights from philosophy into the logics, and make the whole system to scale, not only across computers, but also across teams. And finally, this is where machine learning meets programming language research. And we should make this a tight feedback loop to have any chance at solving the incredible problems we have. Thanks.
Fantastic. Thank you so much. You make it all sound so tangible and real and easy to use. We don't have any questions online, and we're also running very close to finishing time. So we were due to wrap up at 5 p.m. and the venue have said we can stay till 5:30. Is that okay with people? We're about to just start our last talk. Thank you. We can possibly stay a bit later, but there'll be a sound check going on, so it might get noisy. And
yeah,
so
I would say to people in the room, you can ask questions afterwards. So we can
in the pub where we're doing some more bottomless learning.
Absolutely.
Okay, fantastic.
Absolutely. Thank you very much.
Fantastic. Thank you. Thank you. Thank you. Right. So we're on to our very last session of the day, followed by some discussion. And I'm delighted to introduce our CAIO, Dr. MeTTa, and Andre Senna, who's going to be leading this talk online. Andre, I think, is going to screen share now. Did you want to say anything to introduce the talk? We're going straight to Andre.
Okay, so thank you, Janet. Okay, can you hear me?
Yes, thank you.
Okay, I'd like to thank you, and I need to say that I'm very happy to be here today. Just regretting not to be there in Seattle, but anyway. So Let me share my screen. Okay, can you see my presentation?
Yes. We sure can.
Okay. So today I'd like to share with you some preliminary results we achieved while studying the possibility of using 2 DB engines to store a distributed atom space. Okay. We have been discussing in our OpenCog forums for quite a long time what will be a proper architecture to implement a DAS capable of storing huge amounts of data and providing a query API, which is flexible enough to handle AI processes queries timely. Not sure if anyone here have participated in such discussions, but if you have, so you know that we never agreed on a DB engine to use. Basically, because each DB paradigm or each DB management system is good for representing some aspects of the atom space, but fails to represent others. Well, actually, the suitability of representation itself is not the main problem. I mean, we can always hammer a representation, but different DB engines also have different indexing and caching structures, which are good to answer different types of queries. I mean, we have several use cases involving queries to the atom space, and the nature of such queries differ considerably from one use case to another. For instance, we have use case where we need to traverse subgraphs. So we need to query for neighbors, paths, spanning trees, and many other graph-based structure. But we also have queries based in values or texts or regular expressions stored inside nodes and links as properties. So when dealing with huge data sets, we need proper indexing and proper caching structure if we want to answer all types of queries timely. But any DB engine we have considered is great to represent, index, and cache some types of information, but poor to do it for other types. So deciding for some DB paradigm or some DB management system is always a matter of choosing which use case to prioritize. Okay. At some point, we asked ourselves, okay, but what if we don't prioritize? What if we just choose more than one DB engine with complementary features which covers all the use cases we need? Or in other words, why can't we use more than one DB? Actually, this is a very simple question, and I have the answer just right here. First of all, although it's not an original idea, actually, there are lots of systems that use more than one DB. The truth is, it's a bad design, okay? I remember just a couple of months ago, we were working on a project, a big one, very complex relationships among data entities. And at some point, one of the teammates suggested, we could use a separate DB to store this information. And the lead architect was peremptory. He said, using 2 DBs in the same application is asking for trouble. And actually, he's right. Usually, it's a bad idea to have more than one DB in an application. First, because it necessarily introduces redundancy, which is always a backdoor for data inconsistencies, memory waste, performance issues, and many other etc. In the case of DAS, this is even worse because we already have redundancy at a semantic level, independently of how we store information in the backend. So using more than one DB would mean to create another layer of redundancy over a naturally redundant data. And of course, we also increase considerably the complexity of updating operations. Every time we need to update, rewrite, or create new information in DAS, we will need to update more than 1 dB. And finally, of course, we will not, that there is not only computational costs we are raising, we will also raise actual costs as well. I mean, maintenance costs, okay? Actually, I'm pretty sure that we could list 100 other points here if we do a 10 minutes brainstorm in this session. But instead of doing this, let me make a different exercise. What if we don't care about it? I mean, what if we don't care if it's an elegant design or not? What if we can live with redundancy and some controllable data inconsistencies? If we don't care, or more accurately, if we forget about those issues for a moment, then we can write an experimental system using 2 dBs and then present the results here. And this is exactly what I'm doing right now. And that's why I said in my first slide that our results are preliminary. We temporarily forgot about those issues and measured how would DAS answer different types of queries if we store a huge amount of data in a 2 dB backend. If results are promising, we can always extend the investigation to better consider each point listed before, especially the cost to create and update information, which is, particularly for me, the most critical point, okay? Before jumping to the results, I'd like to talk a little bit about 3 points of our test strategy, which are the use case we choose, the knowledge base we are working on, and the database engines we use. So the pattern matcher, we choose the pattern matcher as a representative use case of DAS. The pattern matcher is kind of a query engine which uses the DB backend to answer requests, to answer queries. A query to the pattern matcher is basically a regular expression in the form of a subgraph with wildcards or variables and logical operators like or, and not. The answer for a query is the set of subgraphs in the knowledge base which satisfies the expression given in the query. I have this small example here with a simple knowledge base and a query. And so the query says we are looking for nodes V1 and V2 such that there is a link of similarity between them. So we are looking for subgraphs like this, but not exactly like this, because we also have an AND operator here saying that there shall not be a node V3 such that there is a links between V1, V2, and V3. So the subgraph formed by chimp and human in this example is not a proper answer to the query. But we have other subgraphs that are. Actually, we have 4 subgraphs which are proper answer to this specific query. Okay. Well, that's the basics of pattern matching in the context of our work. Of course, queries can become more complex with arbitrary combinations of logical expressions. I will not enter into details on how the algorithm to do pattern matching actually works. I will just say that in order to answer fairly complex queries from real problems on knowledge bases with millions or billions of nodes and links, we need some kind of indexing and caching structures to help searching the space faster. Otherwise, a single query could take minutes hours or even decades to be answered. The knowledge base, we used, or actually we extended the database of SingularityNET gene annotation service to build a knowledge base with 17 million links. And we tested with 3 queries we wrote on this database, on this knowledge base. Query 1 is a very simple one. Given genes G1 and G2 and Gn, we are looking for some nodes X, which are the representation of a biological process, a cell or cellular component or molecular function or whatever. So we are looking for some X, which is linked to all genes G1, G2 to Gn through a link of type member. Okay, so this is query 1. This is query 2. Conceptually, it's only slightly more complex than query 1, but it contains an OR operator here, which, although is a conceptually simple operator, is kind of tricky for the pattern matching algorithm because it increases considerably the number of possibilities that need to be investigated in the search for proper matches. Okay. So in query 2, we have only 2 genes now, G1 and G2. But now we are looking for either a common biological process X, just like in query 1, or 2 biological processes, X and Y, such that both inheritance from the same superclass Z. Okay. And then we have query 3. We actually don't need to fully understand the syntax of query 3. We just need to understand that now, differently from query 1 and query 2, we are looking for a specific substring inside the properties of nodes. Okay. In this case, we are interested in any occurrence of CoA, which stands for coenzyme A, if I remember correctly. So differently from query 1 and query 2, the searching criteria now is no longer only in terms of connecting of nodes and links. Conceptually, this is the most complex of the 3 queries. And the DB architecture we are using, we choose Couchbase and MongoDB. Although we could choose other engines, we believed this particular choice may give interesting results. We have extensively discussed the use of different DB paradigms to represent Atomspace data. Actually, it's almost a consensus that a key value DB or a graph DB are the best choices for a single engine DAS. But for a 2-engine DAS, they are not a good choice together because they share some of the main pros and cons. So having a key value DB to represent hierarchies and a document DB to represent nodes and links structured information sounds more like a tempting approach. And that's why we choose these particular engines. At this point, I need to say something. I need to explain a little better some point. As I told you previously, I don't want to enter into details on how the pattern matching algorithm works, but I need to explain something about how the queries I presented here become actual queries to the databases. So let me use query 2 just to illustrate my point. it's not like we just turn this whole query into a DB query using SQL or any proprietary query language of the database management system. Actually, the query, as we show here, is an input for the pattern matching algorithm. So the algorithm performs several operations while processing this query, generating hundreds or thousands of actual DB queries. When we use a single DB architecture, all those thousands of queries generated by the pattern matcher are directed to the same DB. When we use 2 DB architecture, some of these queries are directed to 1 DB and others are directed to the other DB, okay? Okay. Before showing the results, I'd like to give you just a quick glance of the test environment, just in case someone is curious about it. We run the tests in a dedicated workstation, and basically we use all the default configurations for the databases. So the results, here we have the mean time and standard deviation of execution time given in seconds for each query in different scenarios of DB backend. Okay, we have the 2 single DB architectures here, one using only Couchbase, another one using only MongoDB, and a 2 DB backend using both Couchbase plus MongoDB. Although query 1 is a very simple one regarding semantics, the number of expressions manipulated internally by the pattern matcher is quite large. So in other words, the time spent in the communication with the DB backend is a lot more relevant than the time spent in the pattern matched algorithm itself. So it's interesting to pay attention to these numbers because they give us a feeling of how fast the DB backend is answering requests. We measured a mean of 2 milliseconds to answer query 1 using the Couchbase and the Couchbase plus MongoDB architectures. This seems very promising results. The time itself, it's small enough to be considered adequate, and we still have plenty of room for optimizations in the DB architecture itself. For example, by turning the cluster of servers and the cache hierarchy. MongoDB, on the other hand, performed a lot worse, but this can be explained by the type of requests required to answer query 1, which is something like, give me all documents whose field type is equal to member. The way MongoDB handled this query is a lot worse than the way Couchbase do it. Of course, to be completely fair, we need to say that these results need to be revisited once we optimized MongoDB properly. But making tests with no optimization in MongoDB doesn't invalidate the comparison between the 2 DB architecture with the single DB ones. Query 2 is a bit more complex, especially because it has a combination of AND and OR, which is slightly harder to the pattern matching engine, as I already said. Here the numbers are too large to be considered adequate in absolute terms, but they show something very interesting. The mean for Couchbase plus MongoDB is smaller than either Couchbase and MongoDB individually. It means the pattern matcher takes advantage of the 2 DB backend by exploring the best each DB has to offer. Actually, this is exactly the sort of result we have been searching for in this proof of concept. And in this sense, the numbers for query 3 are even better, as the mean for the 2DB architecture is more than 10 times smaller than the ones for the single DB approaches. This is because query tree explores a major strength of MongoDB, which is querying structured documents, especially text. Performing such an operation in Couchbase is more expensive. Of course, again, we could create a Couchbase table to optimize it, but that will be a very specialized optimization targeted to just this type of query. For example, a table mapping from words to nodes whose name contain that specific word. MongoDB, on the other hand, is already prepared for such type of query and provides many types of similar ones with built-in indexes. Okay. And then our conclusions and next steps. The main conclusion is that we should spend more time pursuing an implementation of DAS using more than one DB, probably using one key value and one document DB as we did is the best approach, although we may end up choosing different DB management system. Actually, that's why we need to extend our analysis by, for example, we need to consider the cost to create and, even more important, to update the indexes. That's why this is the first topic in our next steps. Although the average response time for the simple queries is small enough to be considered okay, this is not true for more complex queries. So we need to improve this, but results we obtain by running everything, I mean Couchbase, MongoDB, and pattern matcher, all in a single workstation. And hence, an important next step is to properly tune a cluster of servers for MongoDB and Couchbase in order to have more realistic response time. And in addition to tuning the DB deployment, we also need to optimize each of them by creating additional indexes, either by using built-in features such as MongoDB's text searching or engineered index like inverted lists implemented as Couchbase tables, for example. And finally, there is another way to improve query performance, which is an important point we didn't mention in this work, which is the use of a cache hierarchy, which will probably have some layers on our own code and other layers inside the cache system of the DB engine. Well, this is what I prepared for this presentation. Thank you everyone for participating. I hope you all found this subject as interesting as I think it is. Matt, do you have something to add to the presentation?
I
always have something to add.
You always do, you're right.
Or subtract or something. Anyway.
I think I would just say those are, I think, really incredible results.
Yeah, that's a wonderful, very clear presentation, Andre. So thanks a lot for that. It's been a long labor to get to a design like this. I think by yourself, Linus, many folks over the years looking at different ways to make backing store for OpenCog type systems. I wanted mostly for the audience to highlight a certain analogy between MeTTa and the distributed Atomspace, and then maybe get a couple comments from you, Senna, on that after I've highlighted it. So I think in MeTTa, what we're looking at is a very general purpose language, but then to do most useful things, we're going to create domain-specific languages within MeTTa, and this is because the same language that's useful for scripting, say, reasoning control heuristics is not the same as the optimal language for scripting interaction with an external deep neural net or something. So we're creating a very general framework, and then to deal with specific applications, we're doing special languages in there. And this is basically because making an efficient, usable, general purpose AI language is impossible, right? So the best we can do is create a meta language that lets us make languages doing the specific things we want. And then ultimately, the AGI system will figure out how to specialize it for different applications. At first, it's people. And I think the analogy in the distributed Atomspace context is making an efficient, distributed, like metagraph knowledge store that will do everything we need for all AGI purposes, I guess is also impossible, right? And I mean, you and I wrestled with this in the WebMind there a very long time ago, right? Because the graph could be anything because it's an AGI system. It's supposed to learn about anything, but yet, depending on the topology of the graph, you know, how you want to handle moving graph nodes around among different machines for optimal query efficiency it's different depending on the topology of the graph, but by the very nature of what we're doing, unlike a narrow AI system or a typical graph database, we can't really say in advance, this is going to be the structure of the graph because the system's, it's got to learn in unpredictable ways, right? So it seems like even for the applications we have now, if you took, say, natural language learning, like we've talked about with Andres Suarez before, we're looking at reinitiated, or look at the bioatom space, or look at, say, OpenCog Atomspace you get from visual question answering. Each of those may lead to a quite differently structured atom space, and you might want to make different configuration choices for a distributed atom space for each of those applications. So it seems like just like you have domain-specific languages on the meta side, it seems like on the distributed atom space side, we'll have a general distributed atom space framework, which it looks likely to be along the two database lines that you've described. And then we're going to need to make particular configurations of that, say for a bioatom space or for a natural language database or an image-related database. And in the immediate term, it will be, you know, us semi-clever humans on the team to figure out how to make the domain-specific configuration of the distributed atom space. And in the long run, of course, the AGI will monitor the structure of its own graph and then figure out how to reconfigure itself. But I wonder, finally getting to something resembling a question, I wonder how you see this sort of application or graph structure specific configuration of the system in this two database design that you've concocted. Like, does the presence of two databases hurt or help in specializing the system to some particular sort of graph?
Doing this is a matter of using indexes and caching properly. Okay, so we need to separate the indexing stage from the execution stage. This separation needs to be very clear, just as we have with search machines like Google or something like this. You first create the indexes and then you use them, okay? So the point here is for each application, for BioMind, for each application we need to have different strategies to build index and to define how the caching system will work. I mean, I think that's the path to have what you just said, to have a good setup for each kind of application.
So basically, each application may have custom indexing and also may have custom caching policies. Which
surely they will have. Surely they will have. I don't think it's possible to have a general. You just say, I will build those indexes this way, and this will work for everything. I don't think this will be possible. We always have to to know what kind of information we work, and then we build index using this information. Okay, you need to be specialized.
So assuming we deploy this at scale and progress toward AGI, what will happen is we'll initially build indexes and caching policies for what we know the system is going to be doing. And then as it learns and restructures its own graph, then we will see how we need to tweak those things to account for what's actually happening, I would suppose.
Well, they don't need to be built. I mean, you can always do it dynamically. I didn't mean you can't do it dynamically. You can. But at some point, you need to make the decision that, oh, I need to build this index. And then you take some time to build it, and then you start using it.
But it's some code that is identifying a change in the graph. And the code is then making an automated decision like, let's take some processor time to build the index and change our indexing.
Yeah.
Yeah, I think we have a viable path here, and obviously getting from a demonstration system like you built to a real deployed product is a bunch of steps. But last year, when you and Matt gave a talk on this, we were presenting the idea, and now we have some evidence that it actually works. So I think it's super interesting progress. And any other questions for Andre on the distributed Atomspace backend?
And we've none online. We have a couple of general questions, but none for Andre on distributed Atomspace. So should we say thank you to Andre for fabulous presentation? Thank you, Andre. Super clear, beautifully delivered, and great progress, I would say. There's a couple of general questions I'll just ask if people would like.
Yeah, sure.
The first one is for the people attending these presentations. So this is actually a question for the room. Do you think there has been real progress towards AGI in the last couple of years? If so, can you provide examples?
We'll have everyone in the room answer that would take much.
Yeah, not everyone, just if anyone has is inspired. I think we saw quite a lot of real progress today.
I don't think there has been demonstrated skeptic-proof progress toward it. I personally, I don't think we've seen any genuine skeptic-proof progress toward AGI in the last couple millennia. I mean, I think we have real progress on image processing. We have real progress on natural language processing, which even if you think there's a bunch of bullshit around, you got to admit these transformers are generating text it's better than most humans would in many senses. And PQGAN or DALL-E are generating awesome images that you can put in the magazine, right? So we don't have skeptic-proof evidence on AGI of that nature. Neither things are done with OpenCog nor Godot from DeepMind nor whatever is that in my own view. I do think if you believe that this or that paradigm is the right approach, we've seen a lot of incremental progress toward realizing those paradigms, and I think that's true within the deep neural net paradigm. It's also true within OpenCog paradigm or the NARS paradigm. So I'd say within a bunch of approaches, we've seen loads of progress toward getting those approaches to the point where they could create AGI, but none of it is going to convince a true skeptic. I think Mike Archibald had a response here too.
Well, people are talking about that.
You can come up here to the camera, so
It's really short.
show you pretty
Yeah, the only comment was that, well, people are talking about AGI now, whereas a few years ago, they weren't. That's the comment. I was, well, you were, what I meant was the popular media, you see it, more or less ordinary.
So there has been, as Mike said, there has been progress in amount of resources put into AGI, and even more so than that in the amount of hype and public babble associated with AGI. Now, historically in the AI field, excessive hype and resources not coupled with progress has then led to a swing in the opposite direction. So I think that the challenge is to use the current modest upswing in resources and dramatic upswing in hype to get really solid results to then make things take off exponentially. I think that is going to happen this wave around, and I said this before. Like we had a few years, 2014 to 17, huge bursts of progress in vision. 2018 to now, huge progress in natural language processing. And I think we're going to see a similar few years of huge bursts in progress on AGI starting pretty soon. And to me, the progress we've seen on Hyperon from last year's workshop to this year's feels like we're not too far from that. But again, if you believe human level intelligence can only be achieved through like a quantum gravity supercomputer or something, we don't have a compelling, like, demonstrable disproof of that at this moment.
Thank you, Ben. Anyone else got any thoughts on that, Matt?
I would just,
Okay, thank you.
I would just say, I mean, we obviously demonstrable progress is not there, but I think the tools supporting progress is where a lot of progress has been made in the last few years.
Yeah, I mean, it's just if you take the old analog of rocketry or something. I mean, we built bigger rocket engines. We've shot stuff up in the air higher and higher. It's come down. We've got progress in the theory of rocketry, but in the end, if someone believes the Earth is surrounded by a giant transparent bubble, until you shut the rocket all the way into space, you're not gonna
Exactly.
So,
I mean, I think Adam made some points about making kind of a toolkit in a very clear manner, more easier to use, modular in a sense. And I think those components can only help. I mean, I guess that's where I'm.
Great. Thank you very much. Any more questions or comments or observations from the room? You all just blown your brains today. So we only have one more question online, which is where would a total newbie to AGI start in terms of resources?
Well, that really depends what else they're a newbie on. But there is a post on my personal blog which has the incomprehensible name Yuri Cosmotron. But there's a point on my there's a post on my Substack blog which is basically background reading for getting into AGI. So it gives a whole bunch of different links people could follow there.
All right.
Look on my Substack.
So listen, thank you everybody for a fantastic day, for all of your time, comments, interest. Thank you to all our speakers. Thank you to all our team online. Thank you to everyone joining us online. We'll be back tomorrow at 9 a.m. Pacific time, where Ben will be kicking off with the first keynote of the day. Haley, anything you want me to say?
Get out of the building now. Yeah.
Alrighty, well, we'll shut down the video stream and then I'll just tell everyone the arrangements for tonight. But thank you, everybody. See you all tomorrow. Keep the conversation going online.
Thanks, everyone.
Big strong guys that are